Good morning, sir. Hello.
Hello.
Sir, hello. Good morning. So I'll be starting within 1 minute. Please be ready, sir. You can turn on your camera.
Hello.
Yes, sir. Please turn on it. We are ready now, sir. HDM യുടെ മുദ്രമുദ്രകൾ ജില്ലാ കോൺഗ്രസ്
Start करिए. चलो जाए. नहीं जा सकते.
So after much delay, we are about to begin now. and we're very sorry for the inconvenience caused. So I'm requesting everyone to please turn on your cameras so that everyone can see each other. We're going to begin now.
कॉन्फ्रेंस हॉल का जब चलेगा ना वो हमारा साइड है.
दिखा रहा ठीक बोला. यानी सर कहाँ पे ये कुछ काम हो रहा है क्या उन्होंने कैमरा बोलिए.
अच्छा तभी से बोला था क्या है
कल वही आप करिए आपको जो करना है करिए. स्टार्ट करें. लाइव तो दिख नहीं रहा है. हाँ अच्छा
हुआ.
बोलिए.
क्या दे रहा नहीं
इसका तो क्या
हाँ चलेगा सर. चलिए.
Sorry for the inconvenience caused. A very good morning to one and all present here. Today we are beginning with day 2 of AMSE 2024. And for the first technical session, our session chair is Professor J.V. Raman Murthy. And our first speaker of the day is Professor Mohammad Jasimuddin. He is a professor in Department of Mathematics and convener Office of Research AIUB. He has supervised several PhD students and his PhD thesis is from India. He has published several 120 plus journal papers. His research field of interest are mathematical modeling of transport phenomena associated with nanofluid, different non-Newtonian fluid bioconvention, unsteady, steady, free, forced and combined convective heat and mass transfer from various geometries. Similarity analysis of convective phenomena in porous media and clear media using group transformation method. Also, multiple and non-similar solutions of transport phenomena. MHD flows with heat and mass transfer for Newtonian and non-Newtonian regular and nanofluid with microorganism. With this, I request Professor Mohammad Jasimuddin to begin with his talk.
Hello, am I audible?
Yes, sir.
Can you see the slide?
Yes, sir.
Yeah. Thank you. Thank you so much for inviting me. So here in Bangladesh, due to internet connection, you may not audible sometimes. I'm sorry for inconvenience. So this is Professor Dr. Jasimuddin as from Bangladesh. So I'd like to present my recent activities. So the title of my presentation is Group Analysis of Bio-Nano-Convective Transport Problem with heat transfer past various geometries. Bio-nano-convective means bio-convection with including nanofluid. And convective flow means there are two types of convective flow: free, forced, and combined convection. Transport problem, which includes transport of momentum, transport of energy, transport of concentration or nanoparticle volume fraction, and transport of induced magnetic field. So let me go to the next slide. So first of all, we are focusing on boundary layer flow. So what is boundary layer? I think all of you are already familiar with boundary layer. It is a very thin layer near to the surface, over or under which fluid is flowing, where viscosity of the fluid, thermal conductivity of the fluid, nanoparticle volume fraction or nanoparticle volume fraction diffusivity, and microorganism diffusivity effects are important. The flow outside the boundary layer, which is known as inviscid flow. So boundary layer approximation. Why boundary layer approximation is needed? In order to simplify the governing equations. So this is a typical object, fluid flow around a horizontal plate. Here I have shown 4 boundary layers. Delta M is the momentum boundary layer, delta T is the thermal boundary layer, delta C is the nanoparticle volume fraction boundary layer, and delta N is the microorganism boundary layer. Here you see the boundary conditions. Outside the boundary, T infinity, C infinity, N infinity, these are all constant. Several cases may occur. Plate may be moving or flow outside the boundary layer may be moving. So for this particular problem, I have shown U equal to UW. UW is the velocity of the plate plus U slip. Most of the research are use normally slip flow, but from experimental studies, it has shown that slip flow is not adequate to calculate the friction, heat transfer rate, mass transfer rate. So we must include slip conditions, which is velocity slip, temperature slip, concentration slip, nanoparticle volume fraction slip. And here the plate is porous plate. We have used stepping blowing condition, which is different from conventional porous plate. So as I told you before, convection, there are two types of, basically 3 types of convection. Free convection, which occurs naturally, and such as fire engineering, combustion modeling, nuclear energy, heat exchanger, petroleum reservoir. These are some applications area of free convection. Post convection occurs due to external force like fan, pump, blower, and so on. Mixed convection occurs when both free and forced convection are of same order. So nanofluid flow. First of all, I think most of the people are already know what is nanofluid. It is a fluid having dimension 10 to the power minus 9. So base fluid of the nanofluid may be water, it may be rocket fuel, it may be ethylene glycol, it may be any other biofluid or smart gel, ionic liquids. What are the nanoparticles? Nanoparticle may be aluminum oxide nanoparticle, titanium oxide nanoparticle, metal carbide, nitrite, and so on, many more. So there are many applications of nanoparticle. Basically, inclusion of nanoparticle with the regular fluid increase the heat transfer rate, which is necessary for electronic cooling.
Excuse me, Dr.
Yes,
Shyam.
sure. Yes, please.
Sir, can you please turn on the slideshow?
Previous slide.
Sir, yes. Actually, sir, can you click on that slideshow option beside the zoom out option?
Okay. Thank you. Can you zoom out option? Where is
Sir,
that
you can
one?
see below. Sir, right
Okay.
when you see the start menu, right, to the right side,
The-
you can see the minus sign,
right.
the option to the left of it. Yeah, that one.
This one, am I right?
This one, exactly.
Oh, thank you.
exactly.
Thanks a lot.
Now, now it has very good visibility. You may continue, sir.
Thanks a lot. As I told
Sure,
you before, conventional fluid like water, ethylene glycol, engine oil are poor thermal conductivity, have poor thermal conductivity. So researchers and scientists are trying to increase the thermal conductivities. By adding nanoparticle with the conventional fluid bioconvection. Basically, it is a macroscopic convection in a fluid by swimming microorganisms which are heavier than water. These self-propelled microorganisms enhance the density of the base fluid due to swimming direction, which are controlled by different taxes: light, chemical reaction, gravity, magnetic field, torque, and so on. The presence of water normally water is the cheapest base fluid. The presence of water in the nanofluid is very important to keep the microorganism alive. So most of the research paper on bioconvection base fluid are taken considered as a water. There are many applications of bioconvection. Bioconvection can be applied in order to improve mass transport, including mixing of especially micro volumes, and also for improving the stability of nanoparticle. In medicine, as I told you before, pharmacy, cosmetic, agro industry, nanoelectronics, nanophonetics, nano biomedical applications, including drug delivery, cancer therapy, and many more. Okay. As I told you, applications of biofluid. Okay. Now, sample of multi-physical problem for bio-nanoconvective flow. We have multi-physical nano-bio-convection. So, this bioconvective flow may occur in various objects. So, in various media, clear or porous media. Porous media, a media where there is a porosity like sands. These are porous media. And fluid may be two types: Newtonian fluid and non-Newtonian fluid. Sorry. So bioconvective flow first. Now I am going to explain bioconvective flow. First, a biaxial sheet. Biaxial sheet means a sheet which is stretched in two directions. So nanofluid flow have many applications, namely nanobiofluid past biaxial sheet is appropriate for nanodoped biopolymeric coating, for example, aircraft wings. The coating is biaxial stretch in the factory, that is in both streamwise and span-wise. Okay. Sorry. Let me now go to the okay. Now the governing equation for nanofluid. What are the governing equations? Governing equations are highly partial differential equation, so their analytical solution is very complicated. So in order to simplify or transform the governing partial highly nonlinear partial differential equation, we would like to convert them into ordinary differential equation using a suitable coordinate transformation, which is sometimes known as similarity transformation. This similarity transformation can be obtained using various group method or dimensional analysis method or free parameter method. Once the equations are converted into ordinary differential equation, they can be solved using either finite difference or finite volume or finite element or any other semi-analytical methods like differential transform method DTM, homotopy approximation method EAM, homotopy pattern question method, and many more. Sometimes some authors are also use SEBI spectral colloquium method of lines, and many other numerical methods are available. Okay. Let me go to the next topic. Okay, what are the basic equations? The basic equations are conservation of mass, only one equation, conservation of momentum. Since momentum is a vector quantity, we will have three equations. Conservation of energy, energy is a scalar quantity, so we will have one equation. Conservation of nanoparticle volume fraction or concentration, one equation. Conservation of microorganism is one equation. Micropolar equation, if you consider non-Newtonian fluid, micropolar equation, three equations. Induced magnetic field, if you analyze the phenomena involving magnetic field, due to magnetic field, and three more equations will appear, which are known as induced magnetic field. So there are total 13 highly nonlinear partial differential equations. So their analytical solutions are very complicated, sometimes even not possible. So how will we attack this problem? Now, these 13 equations are only for regular nanofluid. So if you add nanoparticle with the regular fluid, we will use one of the two model. One is Bongiorno model, where Brownian motion and thermophorese are included in the energy equation and nanoparticle volume fraction equation. Another is Dash and Tawari model, where viscosity, thermal conductivity, electric conductivity, these are considered as a variable. So both models are popular. So you authors can use any one of them. Okay. As I told you before, governing equations are highly nonlinear partial differential equation, coupled or decoupled. If we consider free convective flow, equation will be coupled. If we consider forced convective flow, equation will be decoupled. So there are many methods, as I told you before. I normally prefer group theory method to convert the PDE to ODE. So group method again can be classified into four types. One is group method based on invariance of the differential equation. Invariance of the differential equation means before the transformation and after the transformation, the structure of the equation will be the same. And deductive group, linear group, scaling group, Lie group, many more, and dimensional analysis. Now, as I told you before, most of the researchers in this area normally use sleep boundary condition, which will give you unrealistic result on the surface of the body, surface of the object. So sleep condition. So sleep condition may be anisotropic or isotropic. Isotropic means one direction. Anisotropic means one direction. Isotropic means direction independent. So there are many sleeps: velocity, thermal, mass, microorganism, and induced magnetic field. And sleeps are relevant to real flows with nanobio or polymer. Anisotropic means two types of sleep: isotropic and isotropic sleep means direction dependent. So in case of anisotropic sleep, anisotropic porous media, we have to use anisotropic sleep as well. In case of bidirectional sheet, we have to use anisotropic sleep boundary condition. And other popular boundary conditions are convective boundary condition, thermal convective, mass convective, microorganism convective boundary condition. So these boundary conditions are basically generalization of the sleep boundary condition. And non-linear radiative boundary condition, convective radiative boundary condition, which I haven't used yet. So maybe this applications of this boundary condition, convective radiative, where convection, convection, and radiation occurs simultaneously at the boundary. So imposition of this boundary condition will open a new area of research. So I haven't used it, so I am planning to use it soon. Heat, mass, flux boundary condition, reaction boundary condition. In case of chemical reaction, if normally when chemical reaction occurs, we have to use chemical reaction boundary condition. Now, what are the methodologies? Methodologies are, first of all, we have to formulate new transport problem. Transport problem may be either internal or external. Fluid flow outside the boundary, outside the object will be external, or fluid flow within a confined region, within a pipe, that will be internal flow. So then we will formulate either new transport problem or we will extend the existing problem. Then non-dimensionalize the problem. Then use of stream function. We will use stream function to reduce the number of dependent variable. So for external flow, develop the invariant transformation using group methods to convert BD to OD, as I told you before. For internal flow, after converting OD, probably I have already discussed this one. Okay. And various numerical techniques, as I told you before, you can use, someone can use a built-in function, or they can write down their own code. There are nowadays some computer algebra systems are available, Mathematica, MATLAB, or Maple. So use any one of these commercial software or your own code to solve the ODE. Probably I have already explained these things. Cool. So this is a typical bidirectional problem, non-neutrino problem. So here I use several convective boundary condition. Sorry, the wall boundary convective, several convective boundary condition and non-Newtonian fluid. Okay, so maybe time is flying so fast. So these are the governing equation based on literature. So these are all PD, everybody know. So in order to get their analytical solution is challenging. So I will convert them. First, I will as I told you, I convert them into non-dimensional equation. Then using group method, I generate this transformation equation 7. Using equation 7, I convert them into ODE. Then ODE Maple 18 is used to solve this ODE. Then these are the some results. Let me now. As I told you before, if you use no slip boundary condition, you will get wrong answer. So the parameters, you see the parameters, there are some controlling parameters. NR, buoyancy ratio, NR is the buoyancy ratio, NB is the thermophoresis, Brownian motion parameter, NT is the thermophoresis parameter, L is the Lewis number, NC and D are the thermal and mass Biot number. So as I told you before, convective boundary condition is the generalization of slip flow. So this parameter NR, NT, NB, Lewis number, NC, NB strongly affect the friction, heat transfer rate, and mass transfer rate. So as I told you, these are some results. So, okay, now how can we? What might be the future work? So in future, people can extend this model in various ways for various variable viscosity, variable thermal conductivity, variable mass diffusivity, or mixed boundary condition, radiative convective boundary condition, and various non-Newtonian fluid, power law fluid, viscoelastic fluid, and second grade fluid, third grade fluid, and some of the mathematicians also trying to find out dual or triple solution and stability analysis of the problem. Although dual and triple solution do not have any physical significance, so I am interested only for single solution. Anyway, these are the possible models. Bioconvective flow along a particle plate, bioconvective flow between two parallel plates. So I am working on this one, bioconvective flow, bio-nanoconvective flow between a disc, between a disc and cone. So bioconvective flow about a snelling cone, bioconvective flow about a needle. Needle may be porous or non-porous. Media may be clear media or porous media. For porous media, we have to include Darcy porous law in the momentum equation only. Okay, these are some selected references. So thank you. If you have any question, I am ready to answer your question. Thank you for giving me the opportunity. So if any one of you are interested to do collaborative work, you are always welcome.
Thank you so much, sir. We are highly grateful with your words and the content that you shared with us, with much of information. Our next speaker is Professor Tankanath Dhamla, who received his master's degree in pure mathematics with Chancellor Gold Medal from Tribhuvan University, Nepal. He is a Humboldtian, being a George Foster Research Fellow for Experience Research in Kaiserslautern, Germany during 2012 to 2014. under the Alexander von Humboldt Foundation. He is a former DAAD alumni and NSER fellow, and he was the DAAD Research Ambassador for 2015 to 2021. Professor Dhamla is the former president of Nepal Mathematics Society and Nepal German Academic Association. I request Professor Dhamla to please begin with his content.
Thank you, madam, for your introduction. Can you see my slides and can you hear me well?
Yeah, it is. You are audible. You are audible.
Okay, thank you, sir.
Thank you.
Thank you. First of all, thank you for inviting me at this important event. And unfortunately, I could not be present physically. Anyway, it is a good time to share with you. And I have seen, there is a group of my students, maybe six there, six there. So today I'm going to discuss about some flow models and their algorithms that are applicable in emergency planning or raw south traffic scenarios. Instead of going into one problem in depth, I am going to highlight few problems. One problem, but in different dimensions. And I hope this will be interesting to all of you. So this is output of research of several years with collaboration, as our announcer madam already announced that I am a homework researcher and that alumni. So it is collaborative work from Germany, and you can see one professor standing over there. So he was from Germany, and there is not only me, there is a big group behind, and I already said there are 6 with you already now. They're in the hall maybe, if they are not gone to the sightseeing. And so I acknowledge all of them. And this is the scenario. This means the Asian, I should say Asian or developing countries infrastructure is very weak usually, and there is no planning of the traffic, metropolitan cities, and traffic demand is increasing day by day there, and because of the lack of planning, the traffic jams are increasing all the time. And we look at from different perspectives, because we want to maximize the flows, minimize the time, and our main strategy is contra-flow approaches, means lane reversals, because some lanes are not utilized and some are overloaded. So we want to utilize them in appropriate way, in optimized way, and this has different applications. And this is just one motivating slide. You can see the flooding, hurricane, volcans, and earthquakes mainly. And this happens. This is a common problem in India, in Bangladesh, in Nepal as well. And the two scenarios you can see. Sometimes we can support the logistics, or we can put some facilities in emergency cases also. These are the motivations of this research in the background. And you can see different challenges, because understanding this real life is really challenging, and once it is understood in some way, we have to make a proper optimization plan and solve them, and again implementation is challenging because of the social scenarios, political influences, and behavior of the people. So these all are the situations. And on the left you can see we have to deal with different situations. For example, if we have a given time horizon, maybe 10 hours or 5 hours or 3 hours, how many people can be shifted at maximum? Or if we don't know that, and we are at some festival time or some special occasions, and there is a huge amount of people gathering, and something happens, and at what maximum point we can evacuate them. And the third point is this is network, and this network is really huge. For example, Kathmandu and bottlenecks. Bottlenecks is really a problem in the evacuation scenario. So finding bottleneck is already a challenging thing. So we don't know the bottleneck. So these different we can see this problem from different angles. But if we can solve one from one angle, then it's also helpful to the another angle. So this what I wanted to show you is because at this conference not only optimizers and not only the discrete optimizers actually, so many diversities is there. So this is very interesting because this problem is not only dealt in network network optimization approach, but different scenarios. For example, somebody do flow simulation, some do variation analysis, purely analysis things, and some do control theory, and some do fluid dynamics, where differential equations are there. And in programming optimization, nonlinear, integer, combinatorial, stochastic, and fuzzy can be any type. And network flow we are interested we are doing is multi-objective and bi-level objectives, multi-commodity or single commodity and single objectives, or only one level can be there. So the problems are difficult because of here I already explained the objectives, and there are parameters may be different because in the usual scenarios parameters may be fixed, but when the emergency happens, our estimated parameters may be destroyed, and all of a sudden something is stochastic, uncertain, whatever be, maybe the situation there. And solutions, continuous solution, I said because of this, the upper part, this analysis approach or equation approach, continuous solutions are achieved, but these are rather complicated because we cannot deal everything in the model, so we discretize the situation, and if we go to the discrete situation, the solutions are already approximated, but the handling issues are little easier. And I said hardness depends on the network, what type of network is that, and what type of attributes are there, and which methodology you apply. This is a basic example you can see for how to model this in network scenarios, in the network flows ways. For example, there are 4 places, and between them there are connections, and in the connection there may be capacities of the roads or large. This is not only limited to the traffic flow, maybe in the communication also this may apply, and transportation also. So there is a capacity, and second parameter with travel time on the connection, or even there may be additional cost on the connection. So there will be different parameters, various parameters. The parameters may be constant or may be variable or changing over the time. So that may excuse me.
It's okay.
Okay, thank you. So there are two formulas already achieved. These are because of which the solutions are becoming easier in particular cases. For example, the first Ford cursor and second Anderson-Philpott both utilize static flow, and static flow means the easiest one because we know everything and we have one solution, and that is repeated over time in the dynamics. So if this is the lucky situation, then we are easily solving the problem, but that is only a rare case. So this is the two-terminal flow, means there is only one disaster place and there is one only secure place. That is again very rare situation. This is easiest one. And the model, there is a flow. Flow is on each arc every time, discrete time, non-negative values. And the first constant so that you have flow conservation when the process is terminated. and there is not non-flow conservation. The flow in may be greater than equal to flow out if it is in the meantime. Okay, so and the flow is bounded by the upper capacities. There is capacity on the road, that is resource. If we have a lot of resource, then we don't have problem. And the goal are, there may be basic two goals. One, we want to maximize the flow. You can see on the left rate, and then we can minimize the time on the right, and the constant are the same. So this is a discrete version. If we want to go into the continuous version, this is everything summation is replaced by the integral, and the amount is replaced by the rate of the flow. And this is sometimes discrete solution is transferred to the continuous solution with some appreciation. So this is one thing we should keep in mind. We have experience in the traffic situation, because you can see from X to Y, going well to X, there is zero travel time. So it is very quick, and that comes to down Y and comes to D, because there is only one travel time, 1 unit. So this is the most favorite situation. But when the flow is starting from any vehicle, starting from S to Y, this is to Y, then this YT connection should be reserved for the lower part flow. So the upper part from S to X should be diverted to D. This is critical, because sometimes we use some connection, and some different time we use different connection. That means whole the day, whole the night, or whole hour, whatever is the evacuation scenario, we have to change the travel paths, travel routes. So that makes the situation very difficult. This is what I am saying. Contra-flow is, you can see on the left, the one side connection is totally empty, because nobody wants to go to the disaster direction, and another is completely full, so everything is stuck, nothing is movable. On the right, if contra-flow is applied, means both directions are used, then for the same direction, because we want to evacuate in one direction. That makes the problem difference, and is little bit smooth. And these are the pioneers, and Pradesh and Siksha in USA. And this the idea of the contra-flow, you can see in this small picture that there are two directions, and they have travel times. These travel times have a good trick, because these may be equal or different. So if they are equal, then they handle this problem. If they are different, we extend the models into the different travel time situations. So this is the basic model they Siksha applied, that they calculate overload degree, means how many people are moving and what is the bottleneck. Depending on that, they give some heuristics, but that is only heuristic and is not optimal solution. And somebody claimed that this is only the way, because if we go to the optimal solution, then that is impossible, because you can see if it is bottleneck too high, then mathematical programming even does not work. So if it is a really large, must go into the heuristic. It is unfortunate message. So you can see how tricky is the contra-flow orientation, because in the expansion of the roads, you can see 6 capacity is here, 2 is here. So 8 is in this line, and then again 8 is coming. So here again 8 is going. So what is use of this Koteshwar Balkumari? You listen it, Koteshwar Balkumari, 8 capacity. So we should be very careful in constructing the road. Actually, this contra-flow problem is NP hard, and is very equivalent to reducible to the 3-set fundamental problem. So now I come to this main slide, that this is just introduction part, and I spent half of the time. And we did in these many directions. The evacuation may be car based or transit based or transit based, and we work on these both and uncertainty scenarios. Also, little bit we have started currently. And contra-flow, I said there are equal travel time on both sides, or they may be different, or they may be variable transit time, depending on the situations, what type of contra-flow you want to apply. when what type of evacuation scenario or network scenario topology is there. And priority based, this is our approach, and we want to maximize the flow not only at the sink, but we want to shift as many evacuees as possible from the source disaster place. So this is intermediate to, as we say, and we have a little bit work, and it's not bad, it's a good work here. And again, we have a different approach, abstract flow. The abstract flow means the main issue in the cities is at the junction, because when there is a connection, there is a flow, but when vehicle has to wait at the connection, that there is a problem. And because of that, the flow is time is heavily increased. So we should realize, from mathematically, we have realized that we should avoid the conflicts and merging as much as possible. Maybe this may cause individual drivers a little bit longer route, but the time is even shorter, because driving longer route is better than waiting long time at a point. That because of that principle, we work there, and also there are good publications. And another approach is because some roads are, as already showed in one of the slides, that some roads are unnecessary and some are very important. So if we want to locate some facilities, some emergency medical, something in the case of emergency, then we should figure out which connections are better to locate and which are not. So we work on that. And multi-community means not only one community is flowing on the network, but different communities from different sources, different things, really have a difficult problem. And the gain loss factors, another issue is while in the network, because maybe in the water flow or maybe in the gas flow or whatever, maybe another things, not only the people, but there may be loss in the way. So our idea is don't lose as much as, and the loss, minimize the loss. And other flow improvements are the following. For example, budget comes. There is a budget. Until now, we did not care about the budget in the contact, because emergency is more important than the budget. But in practice, sometimes budget is also important. So if there is certain budget, we should be limited with the budget in constructing the new roads or redirecting the lanes. So our point is, we want to be limited with the budget in redirecting the arcs. And another is by criteria and by level we are doing there, and this is means government wants one route and people want different. So there are two opinions: policymakers and consumers. They have different customers. They have different opinions. So how to integrate them and how to satisfy both of them at a certain level in using optimization techniques, we are working. It's very important. Another is what we do is we see is speed adjustment, because at the bottlenecks and some bridges the speed is very slow, and because of that traffic jam is increasing heavily again and again. So their speed should be increased, and if we can increase somehow the speed by some techniques, by controlling the traffic little far on both sides, then our traffic is more smooth. So these are the scenarios, these are the directions we are working on. So as I maybe announced that if somebody is interested in one of the approaches, we are ready to cooperate. And but now I want to go in detail, not detail, but little hints to some of the issues, not all of them. Okay. So contravo means, what is it? By contravo, you are very excited, because this is a two-way lane, this is a one-way lane. And with this contravo, we can increase solution a lot, because no contravo means 7, and with contravo we have 15. So this is more than double is achieved with the contravo. So this is very exciting approach. And then partial means we don't want to revert all the lanes, but only the necessary. This is our approach, our model, and with this also we have the same flow, but we have still saving some lanes. These are for facility locations, emergency, logistics, everything. So this is, we are coming to the partial, and this is better than the Padalus and Siksha they initially initiated and modeled the problem basically. So, and this you can see another this I don't want to explain this because you already got the point how to different. I mean, what we extend is from symmetric we wanted to shift in the origin dependent travel time means in which direction the flow is traffic is oriented, that time is taken. So that we extend, and that also improves the solution quite a lot. And another is this is in Kontabo the road capacities are added from both sides, but in our this approach we don't add because sometimes it is not possible to add because some road may be underground, some may be overground, so we cannot add the capacities. But travel time is as the same it was before. But we add some additional nodes and introduce, and then we make new graph and we solve the problem. So another thing what we did is intermediate storage. We wanted to increase the flow a lot, and by introducing intermediate nodes where flow can be stored. So this is the extra term is added where intermediate nodes occupy some flows, and we did it. And this is one of the pioneer researcher with was with us, now is not anymore. And this model is you can see the difference is we add some intermediate values and we add some intermediate node capacity. With this we extend the previous model, and the technique you can see is with the intermediate. I don't want to explain more, but flow at the sink is 24 and flow with intermediate node is 48. So it is again more than 50%, 100%. So this is with the Kontapu intermediate, a lot of improvement is there. As I said, what is the effect of crossing in a merging country? This means I just wanted to highlight that you see this is the flow is typical because flow is V A X D. Here is at A there is a crossing, and on the right at A we avoid the crossing. And because of this, some solution may be lost. I don't want to explain anything more, but this is only the motivation that at A one has to evaluate a lot of time, and we want to avoid this, and we want to avoid the crossing and merging here. But because of that, because of the capacity, incoming capacities and outgoing capacities, the flow may be lost. And how to recover that? We apply one strategy that to recover that lost, and this is we call it temporary repeated solution we obtain, because temporary repeated solution means once static flow solution is obtained, then the dynamic solution is obtained by repeating the static solution. And how we obtain is partial switching. We said partial switching. So we switch the flow at intermediate nodes whenever possible. If not possible, then only the part of the flow we continue to be crossed or merged. Because of doing this, we achieve the same flow as without this approach. So this saves a lot of time, and because of that, flow is maximum increase also. So the next thing what I wanted to highlight and motivate is flow location. Flow location means there are some arcs where flow facilities should be located. And because of that, you can see in this example, because of that, the mathematical deviation is not explained now. Because of that, if somewhere in some arc, some connections flow facility is located, flow is reduced drastically. If at some point it is located, flow is increased, not decreased drastically. Because of this motivation, we did this work. And I cannot go into detail because in this short time, but in all of these approaches, one good news is we have added the intermediate storage idea, and in most of the approaches, intermediate storage is allowed and possible, and we can increase the flow with the intermediate storage as well. And one point is, if we are doing intermediate storage things, we have multi-sink problems, so we cannot solve this problem. So we have to solve this problem with lexicographic ordering. So this means there are priority nodes, and at the priority node we have to shift the flow first, and in the list next. And one of my student, Vishwadikari may be sitting there. He extended this result to the bi-criteria or tri-criteria approach, that all things should be compromised in maximizing the flow. He already presented that there, I guess. So, and this is flow location, what I said. And multi-commodity, I think I explained a little bit before, but this means here you can see in the middle, because from S1 to D1 there is dedicated flow, but in the between they have to share. The flow has to share, and this sharing means now they got problem, because coming from S1 or coming from S2, which flow gets the priority here. So this is a really complicated problem, because this solution integrality will be lost, and max flow min cut property will be lost. So many things will be lost there. So if many things are lost, then our previous solution techniques will not be valid. So everything is NP-hard, and in this NP-hard case, in case of dynamic, of course, there are approximate methods. We bounded cost. There is some cost. Cost means that is related to time, not given cost, or this is solved in time expanded graph, different time expanded expo. This is delta coordinates. We say this time expanded graph is the basic idea to solve these problems, but this is condensed by delta, because decreasing the time and increasing the capacity. So this is one of the approach we can handle multi-commodity flow problem. And there also contra flow applies, and there also intermediate storage applies. So it is both approaches are very surprising. Everywhere they can be implemented. Here intermediate storage can be added like this, and of course the capacity constant at the nodes. Before it was not at the nodes. And maybe time is very close. Madam Sana, how much is time? Do you have time, or I can stop it? No problem. We don't care about the number of slides, but we can stop it if there is no time. So I continue a little bit. So generalized flow means there is a flow loss in between, because if 10 is started here, then this is in the between there is some loss factor. So 10 is multiplied by the loss. So maybe here if 80% loss or 20% loss. So we want to reach some flow from 10 flow from V to Z with minimum loss. That is the idea, and that is the strategy. So how to achieve this? To achieve this, the main idea I want to tell is one motivation, because if main idea is we have to choose the highest gain path, and we have to prioritize the highest gain path for the first time, and then take the low gain afterwards. Because with this you can see, if we choose the highest gain path first and then lowest gain, then we have the flow is with the highest gain 152 and 124. So again here also we can apply the contravo. Here also we can apply the intermediate storage. And highest gain means one property I forgot to explain. Highest gain means the loss while traveling the flow is the minimum. This is the definition. I think time is over. Nobody is speaking. So here are intermediate storage you can see. Without intermediate storage we have very less flow, and with intermediate storage we have a lot of improvement. So you can see there is very less flow without, and with intermediate, this is blue part is because of the intermediate storage. So only block. So this means we have a lot of improvement. So I think I should stop. Sir? Nobody there.
No, no, sir. Actually, we are already having 3-4 minutes, so that's why we didn't interrupt you.
Madam?
Hello.
Yes.
Sir, we are having 3-4 minutes left, so if you want, you can continue.
Okay, this is, we can stop also, but if you are there, then why not?
That's okay.
So I think we can stop it because can leave little space for the discussion because that is more better. If otherwise, okay. So I stop it and I thank everybody for giving the opportunity and listening.
Thank you so much, sir. If there's any question, then you can ask.
If there is any question, yes, please.
No questions? So, shall we proceed? Okay, thank you so much, sir. Thank you so much.
कर लीजिए जो बात करना है ऑप्शन नहीं है
Sorry, ma'am, you have just wait for 2 minutes. We'll be back.
Okay, I can see the participants now.
Yes, sorry, ma'am. So our next speaker is Professor Santana Mukhopadhyay. She's working as a professor in Department of Mathematical Sciences, IIT BHU. She's also acting as the chairperson of Internal Campaign Committee of IIT BHU, and her research area spans over mathematical modeling of coupled dynamical thermoelasticity, magnetothermoelasticity, and viscothermoelasticity, and known for her heat conduction theory. Professor Mukhopadhyay has also expertise in the area of nonlinear dynamics. Her work is highly cited in the area of thermoelasticity. She had been invited as academic visitor by a number of institutes or universities in India and abroad. She has been invited to act as editor or associate editor of several international journals, including Mathematics and Mechanics of Solids, Journal of Thermal Stresses, Computational Methods in Science and Technology. With this, I request Professor Mukhopadhyay to start.
Okay, thank you so much. Is the screen visible to all of you? And am I audible?
Yes, ma'am, you are audible and your slides are also visible.
Okay, so thank you, madam. And I'm really happy to take part in this third international conference on applied mathematics in science and engineering. And it's my great pleasure to take part of this, though it is in online mode. I could not go physically present in this conference, so I'm sorry for that. But anyway, at least I'm thankful to the organizing team and especially Dr. Okudev for inviting me to deliver a talk here.
Sorry to interrupt you, ma'am. Can you please do the full screen of your presentation?
Okay, 1 minute. This.
Ma'am, just click on the option to the right of the plus sign.
Right.
No, the left one. Yeah, this one.
Now it is fine. I think now it, yeah.
Ma'am, can you please kindly click on that option once again to the right of the plus sign?
Yeah. Okay.
In the center of the screen, you can see that
I think
the
now
option
it
to
is
the right.
fine. Right. No, but this is not full screen.
Okay. No, ma'am, just click on that option to the right of the plus sign. Another one? This one. Yes.
Okay. So I have to decrease the. Now I think fine.
It's fine.
Okay.
Thank you, ma'am.
So thank you. The topic of my talk today is the mathematics for qualitative analysis of some heat conduction and thermoelastic models. So the main objective of this is to discuss about the recent advancement of heat conduction theory. I don't know how many participants are there who are aware about this advancement, but anyway, that's why I will try to give a little detail or brief history of this advanced theory, and then I will show that how mathematical analysis can be helpful to understand some aspects of coupled dynamical thermoelasticity that is based on some of these advanced theories of heat conduction. So that's why the plan, I have planned that I will start from the very fundamental law of heat conduction, that is the Fourier's law of heat conduction, which everybody is familiar with. And then I will introduce that this Fourier's law of heat conduction or this classical theory has some drawback. And that is why naturally some non-classical theories have been developed, so that some brief account of that I need to talk. And then I will apply them to coupled thermoelasticity and also advancement of this theory also little bit I have to tell. And then it will be my contribution part from myself and along my research scholars, that I have presented I present the qualitative analysis of some recently proposed models, and then show that I can show that some issues on these developed theories and which needs attention of researchers, and then of course some if there is any queries that we can discuss. So as we all know that the Fourier's law, which is a very familiar, well-established law, and that states for homogeneous and isotropic medium, this is the equation we all know, that Q at a point R at time t is equal to minus K grad T at the same point R at time t. So that is for isotropic medium, and similarly we can have this equation for an isotropic medium also, or non-homogeneous medium. And for that, if this equation is now coupled with the energy equation, that is equation 2, then we get the main our familiar diffusion heat conduction equation, or the diffusion equation 3, where K is thermal conductivity, rho is the density, and C is the specific heat at constant strength. They are the material parameters, and Q is the heat flux vector, T is the temperature, and Q, capital Q, is the heat source if there is any in the problem. This equation, I would like to draw the attention of the participants that equation 1, which is the Fourier's law, and also corresponding the equation 3, the diffusion equation. As we all know that this equation has been used for studying the problem for year after year, and it has a it is actually well established equation, we all know. For any conventional problems can be studied by this equation, but during several decades it has been understood that this classical law gives some unsatisfactory outcomes in several situations. Experimentally also it has been observed. And for that, it is very natural to note, very interesting point basically to note that long back in 1867, Maxwell, while doing an experiment, he has postulated the occurrence of a wave-type heat flow at low temperature, and he suggested that the thermal disturbance is a wave-like phenomenon rather than diffusion phenomenon. And he indicated the modification of Fourier's law for the possibly for the first time. So that means, and naturally, what I said in point one, that some unsatisfactory outcomes comes, and also some theoretical inconsistency also can be obtained, can be found out. So what would be the reason? So one analysis which anyone can find out from the literature, that means people have thought of moving in this direction, that if we consider the equation 1, that is q at a point r at time t is the minus k grad t at time, same point r at time t. So that means this Fourier law implies that the change of temperature gradient or change of temperature made at some point on a body, and the heat flow are the instantaneous effect because at the same point, and also the effect of temperature change will be felt instantaneously everywhere, though with a exponentially small amplitude distant points. So on the basis of that, the first theoretical modification of Fourier's law was suggested by two researchers independently, that is Catenio in 1948-58 and also the Arnold in 1958. And they had given the Fourier's law in this form, equation 4, that is q plus tau del q del t is equal to minus k grad t. So as you can see here, that one parameter tau has been introduced in this equation, and this is nothing but called as the thermal relaxation parameter, or it is a time lag needed to establish steady state of heat conduction in a material element when temperature gradient is certainly imposed on that element. So this implies that heat flow and temperature gradient may not be the instantaneous effect, so there must be a time lag, and this time lag can be thought to be the accessed by the parameter tau. So this equation, since it has been given by Catenio and Barnard independently, but this equation is called as the Maxwell-Catenio law or CV law, CV equation, as the first theoretical modification of Fourier's law. And of course, if it carries the combined even diffusion and wave-like behavior of heat transport, because if this equation is clubbed with that, as I said, equation 2, energy equation, then we can get the heat conduction equation in this form, which one is we can say that it is a hyperbolic tap differential equation. So it can predict a wave-like thermal signal which propagates with the finite speed v equal to root over minus k divided by rho c e and tau. And so the tau is existing in this finite speed. So obviously when tau greater than 0, then it is fine. But when tau is equal to 0 is finite. But when tau is 0, then it can be it is of course the prediction in finite speed. So this modification, that is the CV law, with the introduction of this parameter tau, is a first theoretical advancement of this heat conduction equation. And of course, this equation also has been studied a lot in various fields wherever the heat conduction is involved. So this, this why this has been used, but after that also people, researchers have studied a lot in various directions, and various other modifications also have been established. I can introduce one more advancement, that is the dual phase lag model, which is I'm sorry that name is not mentioned of that person, that is a mechanical engineer, Professor Chow, who has introduced that Q, the law of heat conduction in this form, that Q at a point R at time t plus tau is equal to minus k grad t R at a point t plus tau t. So here an additional parameter, phase lag parameter tau t has been introduced, where tau t is the same like tau in CV equation. And so there are two phase lag parameters or thermal relaxation parameters or decay times, whatever you say, are introduced in this equation. So as we see here, that if in the right hand side tau t is made to be 0, then we can see that q at a point r at time t plus tau t is equal to minus k grad t. So that if I expand this equation, then we can get the CV equation, that is q plus tau del q del t is equal to minus k grad t, where right hand side there is no tau t. So that means this equation, this idea of this equation came from several microscopic interactions during the heat conduction process, and which that means that this not considered that heat conduction is not an instantaneous process, heat flow and thermal gradient establishment. Then there are several microscopic interactions happens inside the material, and that macroscopically can be caught by these phase-lag parameters tau q and tau t. So if I due to the dual phase-lag model, if I consider the existence of tau t also, then of course various models of equations can be found out, and several researchers have studied this dual phase-lag model also. At the same time, this model was given in 1995, and at the same time, more or less during the same period of time, two great researchers, that is A. Green and P. M. Nathi, where Green is a mathematician and Nathi is a mechanical engineer from Princeton University, they have rigorously studied these equations, this heat conduction theory, and also their application to the coupled thermoelasticity problem, and they have developed their theory in a completely alternative way, and where the Fourier's law has been introduced in this particular form equation 6, that is q minus k grad t plus k star. So here grad of t plus k star grad nu, where we can see here two new new constitutive variable has been introduced, where nu is given the name by them as thermal displacement, because nu dot is equal to t can be thought of, and k star is also new material parameter, which is termed as the thermal conductivity rate by that. So this model is actually termed as, after that is termed as the Green-Nathi model 3 or GN3 model. And here, in their theory has their theory has been divided into 3 different categories of theories due to the involvement of the parameter of the parameters k and k star, and that is of course for isotropic case, and similarly can be for anisotropic case. So this therefore from this general equation 6 we can have another 2 model, that is they have thought of that it can happen that k thermal conductivity and conductivity rate, how it is for the material, that if k is much greater than k star, then we can ignore the k star, so that we can have the normal Fourier's law. But also it can happen that k star is much greater than k, then we can ignore k, so that we can get another new equation. So accordingly their equations are called as these models of heat conductions are there 3 we can find out, that is N1, 2 and 3, where 3 is the more general one, and it has they have thought of that this equation can be applied to a wide class of problems, because here k and k star both are there, and that is the most general equation of heat conduction they thought of. And similarly it has on attention of researchers during several decades. After that onwards, and several understanding has been made. And after that, very recently, this GNC model also has been modified in this particular form 8, where this equation like q is equal to minus aq, the left hand side, there q was only at the time r. So here one time lag, of course, by the same concept like CV, that it is one parameter or phase lag or thermal relaxation parameter or delay time has been introduced as a tau q. So this is the form of the equation, and correspondingly we can get the equation 9 as the heat conduction equation by clubbing this equation 8 to the energy equation. And this equation has a form like Maury-Gibson-Thomson equation. So many times it has been called in the literature equation 9 as the Maury-Gibson-Thomson heat conduction equation. Now these are the advancement of the theory of heat conduction. So since my target is to apply this heat conduction equations to couple thermoelasticity problems, so therefore little bit of thermoelasticity, let me tell. As we all know that couple thermoelasticity is a subject of science or technology, whatever you say, that it considers the mutual interactions between thermal and mechanical field when a deformable body is subjected to any change in temperature or mechanical load, etc. Then, as we know, that if a deformable body is subjected to any change in temperature, then the body will expand or contract. And if this deformation due to temperature, non-uniform temperature, is permitted to occur freely, then no load or stress, additional load or stress is introduced inside the structure of the material. However, in the cases where temperature deformation is not permitted freely, then internal stress is created, and that is called the thermal stress. So this additional thermal stress will be developed, and that has to be taken care of. And conversely, if the material is compressed or expanded, then the volume change is accompanied by heating or cooling. That is a general consequence we all can consider. So coupled thermoelasticity deals with these two-sided effects, that is change in temperature, mechanical field will be disturbed, and also vice versa. So this is the understanding of this particular subject. They do not but uncoupled thermoelasticity deals these type of thermal stress problems in a different way. That is, there is no coupling in the deformation term due to temperature effect, but couple of thermoelasticity theory considers both the effects on simultaneous effect of this, and it is of course a growing area of continuum mechanics and proves to have a broad interest in theoretical as well as practical research due to its vast application in science and technology. So it is, since this is we are considering the coupling effects of temperature and mechanical field, so it is of course we can think that this subject is a generalization of both theory of elasticity and also the theory of heat conduction. And so the first satisfactory formulation of this couple thermoelasticity theory was given by Biot in 1956. This theory, of course, is based on the classical Fourier's law of heat conduction. But it is worth to mention that Biot's thermoelasticity theory is considered as an elegant framework for investigating variety of issues that involve coupling effects of mechanical thermal fields, and it has been widely and successfully applied to the conventional heat conduction problems. Anyone can go through literature and find that it is there, lots of application of Biot's theory is there. However, some observations on Biot's model also has been observed during these decades. As I said, that it is based on the Fourier's normal classical Fourier's law, and it has been observed that Biot's theory also has limitations, and it is applicable only to the problem that involve large spatial dimension and long time response. But it does not provide an adequate or sufficient description of solid response when subjected to high heat flux, rapid transition heating, such as short laser pulses, and also when the temperature is very low. So the even the heat conduction of many nanoscale devices, that size effect, etc., phenomenon, which are also not captured by this conventional theory. So for that, we have several review articles, books, etc., in the literature available, and can find this one. So naturally, this coupled thermoelasticity theory also has been extended or generalized in various forms, and various researchers are involved in this particular area, and we can find out that some models of extended models of thermoelasticity are given by the researchers like Lord and Salmon, Green and Lindsay, Sao and Chandrasekharia, and also one triple phase like thermoelasticity concept also is given by Rai Chaudhuri. And the recent model of similarly, that as already I mentioned, that Green and Nagdi has given types 1, 2, and 3 thermoelasticity theory, and very recently on the Mori-Gibson-Thimson heat conduction equation, that thermoelasticity has been modified by Quintanilla in 2019 has been given. So now this is the introduction part. Now what I want to say, because my part is that my main motive for today's talk is that there is advancement in theory of elasticity and theory of thermoelasticity or heat conduction. and various models have been proposed, like several heat conduction equations we can see, and similarly thermoelasticity theory. I have not given the basic governing equations because that will take some time, and due to shortage of time I have not given the basic equations of Bayes theory. But I'll start with the most recent model of thermoelasticity, that is the Mori-Gibson-Thomson thermoelasticity, which is given by Quintanilla. And from by considering this model very recently, we have shown some qualitative analysis of this model, and as a special case, we can derive the consequences in the other various other models also. So that means let us see that how mathematics can help us to understand the status of this thermoelasticity theory or the heat conduction equation like Mori-Gibson-Thomson. For that, let us consider an isotropic, of course, we have considered in this work, that homogeneous thermoelastic material which is enclosed by an open connected set, and that, let's say, E closure is the closure of this domain, and boundary is E boundary of these are classified at delta E and E respectively. And in three-dimensional equivalent space, now if we consider the rectangular coordinate system, then the MGT models, the basic governing equations for MGT model is of this form. First equation 10 is that equation of motion, and second equation is the heat conduction equation. I have directly written the governing equations, but there are the constitutive relations, etc., and that can be clubbed together to get equation 10 and 11. So these two equations can be considered as a displacement temperature system of the equation due to the MGT model. And as I have said, that since this problem is considering the coupling effect of temperature and mechanical field, that you can see from by looking at these equations, because equation 10, if I neglect this part, that is beta theta comma I, that is the temperature part, that theta is the temperature above a reference temperature theta 0. So if I neglect that this term is not there, that is the last term in the left hand side, then this equation is nothing but our normal equation of motion, or the wave equation. And similarly in one-dimensional case, but here we are having the three-dimensional equation system. Similarly, the heat conduction equation, we have a coupling effect with mechanical field. That's why in the right hand side, the second term beta theta 0 ui comma I dot is the term has come into existence in this equation due to the mutual interaction with the temperature and the mechanical field. So if one goes through the development of the theory, then we can find out how these equations are coming. This is a very complicated way of deriving these two equations, but we have considered this equation by considering the MGT heat conduction equation. So now and we can see here that, as I mentioned, another two, three models. So we are going to analyze this model, and from that, as a special case of the form of this equation, we can see that here k star, tau, q, all terms have been already mentioned. Beta is the thermal relaxation parameter, and rho cv already we know. So due to the, if I consider this tau q equal to 0, in this equation tau q equal to 0, then we will get the, and also k star is equal to 0, then Biot model, that is the classical model. And if I consider k star equal to 0 here, then we will get the equation that is due to the first the modified thermoelastic theory after Bayes theory, that is the Lord-Salmon theory, which is based on the first modified heat Fourier's law, that is the CV law. And also we can get that tau q equal to 0, then we get that GN3 thermoelasticity theory. So, so here in this work, what we have done, the domain of influence results under this MGT theory. So what we can what we have shown here, maybe I will come to this slide once again after a little bit description that what we have done basically. So now only I don't want to waste time here to tell the main conclusion. So what we have considered that these two equation 10 and 11 we have taken as the basic governing equation of this system of a thermoelastic system. So for a simplicity, we considered that introduce that phi as a scalar potential of displacement field. So u I is equal to phi comma I, so that these equations are from displacement and temperature has been reduced to the form equation 12 and 30, where the basic field variables are phi, that is the scalar potential and temperature. And we assume that the material constants in general, for most general materials, this is the properties to be satisfied, so that various material parameter lambda mu are the Lamé constants, Cv rho etc. are satisfying this, that is the positivity of the parameters. Then for convenience we employ the dimensionless variables so that so many parameters are there, and finally we will get the equation in this form, so that we are having now less number of parameters, but they are all parameters are now clubbed with a parameter epsilon, which is called the thermoelastic coupling constant, which involves all the other parameters like mechanical beta, where beta is equal to 3 lambda plus 2 mu alpha t. So that is thermoelastic parameter. Theta 0 is the reference temperature, rho C1. So all variables, all parameters are there in the epsilon, where epsilon is of course a non-dimensional parameter. And similarly, we have one beta 0 and tau q. They are also now dimensionless. So these two equations are now in our hand. And now, since we are going to study this problem as a whole, for that we have considered a very general initial and boundary conditions, since theta and phi are the constitutive variables. So here, with respect to theta and phi, we have considered the initial conditions and also the adjoining boundary condition in this form. That is the very general form, not homogeneous but non-homogeneous type of conditions we have considered. Now, some one or two definitions we need to say to find out or to mention what we have actually shown in this particular work. So that is, let us consider that the set D0T, where D0T is called as the support of thermomechanical load of the present system of thermoelastic system. That is, for any x belonging to E bar, that when x is belonging to capital E, that is the inside the area, then either these conditions we have considered, that theta 0, phi 0, etc., and also we have this temperature, and also the this phi comma ni, that is the normal derivative of phi is equal to gxt. So that one of these is 0, or one of these is at least one of that condition is non-zero. So that means for when x is belonging to the material inside interior point, is the interior point of the body, then at least one of that is non-zero. So that there is a cause of interaction. And similarly, when it is a boundary point, then either g or theta dash is equal non-zero. So that means we want to say that there is a cause of thermoelastic interactions. So, and the set of all the points are called as the support of thermomechanical load. Means we are understanding that the body is under the action of some loading, that is in terms of temperature, mechanical, etc. And then another defining at dt, where dt is equal to the set of all points at any time t, dt is equal to set of all points of E bar, closure of E, such that the open ball with starting with x and the velocity nu is non-zero. So this is nothing but mathematically this is equation 10 is the domain of influence, but we can say what is domain of influence actually. That dt defines the set of all points of E bar which can be accessed by these thermomechanical disturbances propagating from D0T, because we have told that D0T is the cause of disturbance. So starting from the D0T, and that is why we are thinking that this is non-zero, that is disjoint set, because this, of course, the whole set D0T and the open ball are not disjoint. There is a disturbance and the points affected are there. So therefore, overall set of all points which can be accessed by the disturbance propagating from D0T with a speed not greater than nu is considered as the domain of influence. So if it is so, this on the basis of these two definitions, what we have shown here, that if phi and phi theta is a pair of smooth solution of the present mixed initial boundary value problem, and if the set dt given by equation 20 defines the domain of influence at time t for the thermomechanical load d0t given by equation 19, as we have shown, equation 19 is d0t and equation 10 is dt, then we have shown here that theta and phi equal to 0 on e bar minus dt. So that means beyond dt, that is which one is called as the dt is called as the domain of influence, that beyond dt there is no effect of disturbance. So that means when nu is get and for that we have where nu is the nu we have taken here for this nu is the velocity with what this is the disturbance is propagating, and if that subjected to the condition that phi and theta 0 inside a point, means all points cannot be disturbed by this present load. If nu satisfies that it is greater than 1 plus epsilon 2 b0 and 1 pi tau q, but here we have to consider one condition, that b0 which is related to the thermal conductivity rate, and tau q is the relaxation parameter or phase lag. This condition 22 is satisfied.
Sorry to interrupt you, ma'am.
Hello?
Yeah, sorry to interrupt you, ma'am. We are running short of time, so
Okay. I am main point I have told. So therefore, that's why I don't want to go to the details of this proof. It was a big challenge for all of us. Means my student and this and some collaborator were there. So this one was challenging to prove from this set of equations, from this governing set of governing equations, and establish for this type of support, for general type of support. But that means whatever be the cause, if there is a cause of disturbance, then we wanted to say that there is a velocity of propagation, and after certain time this is 0. So that means you can say that speed of disturbance is finite. So therefore in this work we have established completely mathematically by nurturing the set of equations and the conditions, whatever is taken. So whatever condition can be taken, because these initial and boundary conditions are taken in a more general way. So we can see that main conclusion here we find here that under MGT thermoelasticity theory, we consider those governing equations, then the thermoelastic disturbance propagates from the cause of disturbance region, that is the domain d0 with finite speed equal with a finite speed, and the maximum speed is means the finite speed, and that is equal to the maximum value of this. So that means maximum speed is given by maximum of 1 plus epsilon 2 b0 and 1 by tau q, where these all parameters, about these parameters I have already told. So that means the velocity of propagation due to this under this theorem is finite, which one was not there in the case of Byrd's theory or GN3 theory, because that also has been analyzed here, that when tau q is equal to 0, then we can see the maximum speed is infinite, and tau q equal to 0 means Byrd's theory, and also in case of the GN3 Grignard-3 theory. So, and in this case it is coming out to be infinite speed, whereas in this present model it is there. Similarly for LS model also we have from this result it can be derived that the domain of influence is infinite for classical theory as well as for GN3 theory. However, for the present model, that is if we introduce a parameter tau q in the governing equation, then only you can see the finite speed of propagation of any disturbance propagating in the body. So this was the good analysis, and we can say that for any problem if we consider, then GN3 theory, though it has been rigorously modified from the classical theory, but it still has a drawback, and where classical theory also has a drawback, and both are having the similar type of drawback of infinite speed, which is not there in LS model and GN3 model. So similarly, we have another result we have presented, we have established. So there we can, whatever I have told with the respect to a problem, I can show that in this problem we have considered the propagation of plane wave propagation by considering the same set of equations. And so that this one is an explanation of what the domain of influence theorem we have told, that if we consider the wave propagating through the medium, then the situation of plane wave by considering the solution in this form, to understand the study of to understand the wave propagation through the medium, we consider the solution in this form, so that this relation we can get. And we have obtained distance of 3 that first and 2 modes of longitudinal has the therefore we have elastic mode and thermal mode longitudinal loops. And here we have studied completely analytically and as well as with numerical results, and we have found out here analytically whatever we have found out in this paper, like the domain of influence theorem, that propagation of thermal wave is finite under MGT model, that has been showed here. So one can see from this particular figure that so that we can analyze all the models. So that means the in first figure, this is the elastic mode longitudinal wave. The behavior of longitudinal wave is like that wave this is the omega with the velocity of elastic mode wave with respect to the frequency. So if we increase the frequency of disturbance, then we can see that all the models are showing after certain values of frequency, it is becoming finite under all models. Though in BIOT model and GN3 model, we can see they are having little different value as compared to LS and MGT model, though the values can be seen more or less very similar, because only at the fourth point they are differing. However, we can see a remarkably different result in case of thermal mode wave. We can see here that what is happening in elastic mode wave is not happening in thermal mode wave, because in thermal mode wave, if we increase the frequency of vibration, then we can see that LS model and MGT model are ultimately finite speed like your elastic mode wave, whereas the BIOT model and GN3 model is predicting infinite speed, means the increasing behavior of speed with frequency, which is quite unnatural and should not happen. This one, there is no manipulation or say approximation. This is the main result we have observed, and this matches completely with our domain of influence results. So these are the observations of by various thermoelastic models, and I have wanted to find out that completely with the help of mathematical tools, and though these are not always straightforward, we have to do a lot of manipulation, and we have found out the main issues, that the classical theory, of course, we have observed that there are some limitations and not applicable to some situations, not everywhere. Large spatial dimension, it is fine, and long-term behavior. However, whenever we are considering instantaneous or transient type of problems, there we have the problem, and so therefore several modifications in terms of theoretical elasticity or heat conduction are there. However, all times the modified theories suffered from limitations. I'm sorry, I wanted to mention one more thing, that here, as I said, that that this finite domain is possible only when this particular green color, that this condition is satisfied by the material parameter. So that means in MGT model also, finite speed can be observed only when the material parameter B0 is less than equal to 1 upon tau q. This condition is satisfied. So therefore, we can say that for all materials, it may not be possible to have the finite domain of influence. So therefore, this conclusion we have observed, and I want to highlight that modified models also are suffering some sort of limitation, means conditional, subjected to condition only, it is showing the consistent results. Otherwise, it is again having some problem like your classical theory. And also, we can, I have just observed, I have only shown the one aspect of qualitative analysis of this in this way, but there are lots of analysis available, like in terms of well-posedness, stability of models, etc. And we can see that that these modified models are also having some sort of limitations, and which needs attention of researchers, and that maybe sometime from the scientists and mathematicians we can expect that what can be the actual form of fluid conduction equation. And of course, I am thankful to the many that one of my collaborator Ramon Kunjanila and my research scholars, and also the ACRB for financial support. So thank you so much. These are the selected references, and thank you so much. And I'm sorry if I have taken more time.
Thank you so much, ma'am. If there is any question, then
I am always happy to answer. In the audience, I can see, I think Professor Chakraborty, Snehasi Chakraborty from NIT Rourkela is there. So is there any question from audience? I'll be happy to answer.
Okay. Thank you so much, ma'am.
Thanks to you also, and I'm really once again thankful to organizer for giving me the scope to interact and talk to deliver this lecture. Thank you so much.
Thank you. So our next speaker is Ines Karakis, who is currently affiliated with Queen's University Belfast and Center for Plasma Physics. His PhD in science is from ULB, Belgium, and he has been the invited membership of the Natural Sciences and Engineering Research Council of Canada, Discovery Grants Program, Physics Evaluation Group for 3 years. He was also the member of editorial board member in Scientific Reports, Nature, EBM for Fluids and Plasma Physics. He was the editorial board member of Open Plasma Physics Journal, EBM for Plasma Physics. He has supervised more than 7 postdocs and 5 PhDs. He has also served as external thesis examiner of more than 13 theses. He has given 150 plus articles in referred journals, 60 plus papers, and had delivered more than 30 talks and 45 plus contributed talks and poster presentation in international conferences. We welcome you, sir, and present.
Good morning. Can you hear me?
Yes, sir.
Can you? Oh, perfect. Excellent. So let me share my screen. I take it you can see my screen right now? Just a minute.
Yes, sir. Yeah.
Yes, so share screen, and I think you will have it right now.
Yes, sir. We can see your screen.
Excellent. Okay. Thank you. Thanks for this generous introduction, actually. To be honest, I've changed affiliation recently. So this is work to be presented, actually, based on my work with my research team in the Space and Planetary Science Group, actually at Khalifa University in Abu Dhabi, in the United Arab Emirates. I also teach as a professor at the Department of Mathematics, actually, at Khalifa University. So what I will present is, say, recent work carried out in collaboration with, say, Kuldeep Singh, Steffi Varghese, and then my good collaborator Frank Verheest from Ghent, Belgium. Before I begin, let me thank from the outset, actually, the conference organization, in particular, Dr. Appledev, actually, for giving me the opportunity to be here. Now, what this talk is about, as you see on the title, is about nonlinear wave models in space plasmas. I would like to present an overview of recent results. This is introductory level talk, actually. My ambition was to avoid, say, complicated mathematical language and just present, say, a few main lines on how mathematical theories can help us with, say, investigation of nonlinear waves that are observed, that occur in space plasmas. So in the beginning, I will just give you a brief introduction introduction actually on what the underlying motivation of this talk is about, space observations and phenomenology on nonlinear waves. I would give a short classification of the, say, names of nonlinear waves and how these, say, are applied in space plasma observations. Just the basic modeling principles for electrostatic solitary waves in particular. I would like to discuss some new types of electrostatic solitary waves, and then I will present our very recent work of the last few months, actually, on multi-ion plasmas in planetary magnetospheres. Finally, I would just hope to leave you some overview of open questions. What are open questions in the field and what are future perspectives? Now, nonlinear waves, if one looks on, say, Scopus or Reuters, actually, are a widespread paradigm, in particular in space plasmas, which is an excellent testbed, actually, for, say, nonlinear theories. If we just type solitary waves on any astrophysical and obviously mathematical and physical journal, actually you get an abundance of papers, say, recently. Our focus will be on electrostatic solitary waves, which I would like to introduce in the following. First of all, what are solitary waves about? In general, solitary waves are localized excitations. Think of localized form. Think of a tsunami wave, if you wish, in the sea. So this picture is a widely cited picture from the coast of Hawaii in the United States. This comes from a paper by Mark Ablovitz from the University of Colorado. And you see solitary waves propagating and actually crossing through each other. What is remarkable is the stability of solitary waves. They possess, say, significant stability properties. They might interact with each other and preserve their shape through the interaction. The same happens when they are subject to external noise, external perturbations, etc. The first observations were in hydrodynamics. Again, this is a satellite image of a train of solitary waves. So what we see in the middle of this picture, actually, we see a train of solitary waves crossing the Straits of Gibraltar, which is actually, hope you can see my narrow piece of ocean separating Africa from the European continent. And you see a train of solitary waves, and you see a train of solitary waves that is crest to crest in this roughly 11 kilometers. So you see that we can have waves, if I remember correctly, it was roughly 11 kilometers. So that can have waves in different scales, actually, in different areas of science and physics. Back to plasma physics, which is my main research focus. You will see. I apologize for this noise now. You will see, say, the detection of solitary waves in the laboratory in Queen's University Belfast, where I was until recently, and you see results from laser plasma interaction experiments. Keep in mind what I'm emphasizing in the bottom right of this plot. So you see this bipolar form of the electric field, a minimum followed by a maximum, and then a pulse-shaped excitation in the ion fluid speed and the particle density, actually. Again, we see similar type of, say, bipolar fields, as you see me highlighting at the bottom right, in say, numerical simulations. In this particular case, these are big particle in cell simulations, actually, of plasma expansion into vacuum. So we see that these bipolar structures appear spontaneously in different contexts, wherever, say, a plasma in the auroral region, that's the region near the Earth's pole, framework relevant.
We see these observations, the early observations of bipolar electric fields actually recorded by the satellites. Again, some data analysis from say the same satellite data. This is, if I'm right, from the OTO satellites, reveals this kind of bipolar electric field.
Structure actually, which has a maximum and a minimum, and then a flat area in between. And then this seems to be associated with flat-shaped kind of pulse. In the electrostatic potential. I will try to explain this theoretically in a few minutes. Again, there's a number of theories actually which have followed to explain these observations. These are observations from the more sophisticated cluster satellite on the left, and you see these solitary waves in the circle here, but of inverse polarity. In this case, you have a maximum and then a minimum. And then you have this distorted kind of shaped solitary waves, which you will see in the middle circle, actually. So we see different types of solitary waves, different types of electric field bipolar forms, and obviously this is a challenging topic for theoreticians. This is really something asking for, requiring, say, sophisticated mathematical theory to explain this, the occurrence, the simple existence and the propagation characteristics of these solitary waves. What I'm showing you on the slides are different manifestations of the same problem, actually. So keep in mind this structure here, which is what we call the bipolar field structure, and then the pulse, that you see at the bottom, which represents the particle density excitation, disturbance, actually. More recently, we've been able to send spacecraft, space missions. This is a recording from the Cassini mission near Saturn, the planet Saturn. This image recording comes from the Enceladus. That's one of the satellites, the moons of Saturn. And you see again these bipolar electric fields actually occurring there. So there seems to be a generic kind of pattern. Again, we see such excitations actually near Mars in what we call the induced
the Maven mission, NASA's Maven mission
of Mars. And you see these bipolar structures, say, occurring. This is data from Mars. So how can these be explained theoretically? What is interesting is that what was observed on Mars was both polarities. You would see this standard polarity of the electric field, but you would also see the reverse polarity occurring at the same time. This is not a contradiction. This can be explained physically, as I will try to show you in the following few slides. So, first of all, just the background. Keep in mind that in the Coulomb gauge, actually the electric field is minus the gradient of the electrostatic potential. So, say in simple mathematical terms, if you take the upper function for the electrostatic potential, consider the derivative, multiply by a factor -1, reverse the sign of the derivative, in other words, and you get the structure at the bottom. So you see that if we seek for bipolar structures in the electric field, this is the same thing as looking for pulse-shaped excitations of the electrostatic potential. In the same way, if I flip the polarity, in other words, if the upper pulse becomes positive, then the bottom pulse will reverse its sign, actually. Now, if on the other hand you obtain a monopolar structure, which is a different type of excitation, which I'm highlighting now at the bottom right for the electric field, then this represents transition from two different finite regions on top. Some of you might recognize
under the name of a
this as what
kink
appears
soliton actually
under the
in
name of a kink soliton, actually, in nonlinear physics. In plasmas, this is called the laminar
So both of the
shock, say,
structures at the bottom
excitation.
are
So both of the
observed
structures at
all
the
the
bottom
time
are
space
observed all the
observations by
time in
missions and
space
satellites, and the
observations by
structures
missions and
on the
satellites, and the
top
structures
actually can be obtained
on the
through
top
mathematical
actually can be
theory, which I
obtained
will
through a
try to
mathematical theory,
present
which
to
I
you
will
right
try
now.
to
I'm taking a
present to you right now.
simple
I'm taking a very simple and actually the simplest,
the
the most
theory.
fundamental,
Those of you
say,
who are
version of the
familiar with
theory.
plasma
Those of you
will
who are familiar
realize
with
that
plasmas
plasma
will realize that
number of
I'm
approximations and
say
considering
adapting a
ions
number of
in the plasma as
approximations.
a
I'm
cold
considering the
fluid,
ions in the
temperature of
plasma as
the
a
ions is
cold
neglected.
fluid.
I consider
Temperature of the
continuity
ions
of the
is
ions, the
neglected.
momentum of the
I
ions,
consider
the
the
second
continuity of
equation,
the
the
ions. The
right-hand
momentum of
side
the ions in the
contains
second equation. The right-hand
derivative of
side
the
contains
electrostatic
the
potential phi.
derivative of the
These
electrostatic potential
equations are
phi,
coupled
and
through
these
Poisson's
equations are
equation actually.
coupled through
Then I
Poisson's
consider the
equation, actually.
electrons in the
And then I
background,
consider the
given that the
electrons in the
electrons have a
background.
very
Given
low
that the electrons have a very low mass, I take them to form a cloud at equilibrium. The electrons are
can
simply
be given
thermalized,
by
and they
a
are given
standard,
by a
say,
standard, say,
expression. The
expression.
standard
The
hypothesis at
standard
this stage would
hypothesis
be
at
to
this
take the
stage would be to
electrons
take the electrons to
obey
obey a
Maxwell-Boltzmann
Maxwell-Boltzmann
equilibrium. We'll just go one step further actually
on
by
equilibrium.
introducing
I will just go one step further, actually, by introducing a
distribution
non-Maxwellian, a
function, which in this case is
non-thermal,
called the
say,
kappa
distribution function, which in this case
Okay.
is called the
For those
kappa
of you who
distribution
are
function.
familiar with
Okay. For
plasma,
those of you who are familiar
the
with
scaling
plasma
quantities are,
science, again, the scaling
say,
quantities
defined at
are,
the bottom of the slide. In
say,
particular, the
defined at the
speed
bottom
is
of the
the
slide. In particular, the speed is the
scale is normalized by
is
the
scaled, is
plasma sound
normalized by
speed, and the time
the plasma sound
variable
speed,
is
and the
normalized by the plasma
time
period or the inverse plasma
variable is normalized by
frequency,
the
and
plasma
space
period,
is
or the inverse plasma
normalized by the
frequency, and
Debye
space
length.
is
What one
normalized by the Debye length.
obtains
What one obtains, so I will use this system of three PDEs actually as a basic system as my working horse to proceed, say, in this introduction. First of all, linear analysis. Let me consider harmonic waves. I have a certain wave number k, and I have a certain frequency, the angular frequency omega. So the dispersion relation comes out to be like this, and then what let me see just a minute, what I what I obtain is the dispersion relation that you see on the bottom right, and actually the different curves represent different values of the Maxwellian, say, Maxwellian or non-Maxwellian electron distribution. So we see that smaller values of kappas, which represent deviation from the Maxwellian, say, equilibrium, result in a strong modification in the phase speed of the wave and the angular frequency, actually. If we move towards a nonlinear analysis, the standard way to proceed with a traveling wave approximation is to consider moving coordinates, which will be given by x minus mt. Traditionally, we call m as m for Mach number, say, replicating what would be the case in acoustics, actually. Mach, because the solitary wave speed is normalized by the so-called plasma sound speed. So x minus mt is some sort of Galilean transformation, except that we have frozen the time dependence. Why? Because we expect to find stationary profile excitations, and this is what we're after. Keep this very funny with the time flies. What comes out after a lengthy algebra is a closed relation in this form, which is an energy conservation looking like.
It looks like an energy conservation equation in mechanics, except there's no time. Time is right here for the right side. Phi could be, let's say, a displacement in the phi inside could be
So you should see V capital
say kind of a mechanical potential.
the dimension which represents, say, kind of a mechanical function in these coordinates, actually. The plasma density, the ion density is given in terms of phi, and the ion fluid speed is again given in terms of phi, with parametric dependence on capital M. For this notation, here you still V bottom right is actually should be M, capital M. So M is one parameter, and phi is what we're looking for. This equation can be solved numerically, not analytically, and what we obtain is precisely a pulse-shaped excitation for the electrostatic potential, which is what we were looking for. And keep in mind that this theory gives me a certain, say, existence region in the parameter M for the solitary wave, which come from reality arguments. If I go back to the actual expressions, the reality of the variables, that means that every variable, actually, the ion density, the ion fluid speed, and the electrostatic potential should be real functions of space and time. Reality might be violated if some conditions are, let's say, violated, and in this case, this gives me some extreme cases, extreme curves like this. The bottom curve is the red curve, which shapes, and in shading I obtain the electric field, and then applying the formulas I get the density and the fluid speed actually for the ions. One might wonder what's so special about this, say, theory. This is a theory that is a few decades old. Why am I presenting this now? Well, it turns out that there is a little bit more in this theory. It was observed, it was a few years ago by Sasha Dubinov, a Russian theoretician, actually, that the topology of the curve can be different from the standard curve that you see there. And what I see is a solution which will have a distorted shape, actually, on the
and this situation happens in cases where
I see on the right side, and this situation happens in cases where the solution is allowed to have a very strong amplitude and a very high Mach number. Very, say, it's very fast. The solution will be so what I see at the bottom right is a distorted pulse, actually, for the electrostatic potential, totally distorted, resulting bipolar form of the electric field, and then totally different, say, phase-space topology in this solution. This is from a work of ours, where we try to show that this solution can be possible in plasmas with a small number of, say, species. I will keep it short, actually. I will try to conclude in the next 5 minutes. Now, what seems to be the case is that the structure of these electrostatic solitary waves was observed since years ago in space. We've spoken to the main author of this article, actually, Jolene Pickett, who said we would observe these solitary waves all the time, but we thought those were trains of such standard solitary waves. And again, a different kind of structure which might come out of the theory is this flat-shaped structure that I see here. Now, moving fast forward towards our recent, say, work, what we considered was a 2-ion and 2-electron non-Maxwellian plasma configuration motivated by observations on Mars in the last 2 years. And what we considered in a recent paper, this paper is currently under review. It was submitted to the Astrophysical Journal, say, 3 weeks ago. What we considered was a more sophisticated, say, fluid system, having 2 different ions, 2 different types of ion fluids, a positive ion fluid and a negative ion fluid, coupled by Poisson's equation. That you see at the bottom. Keep in mind that delta is the density ratio of the negative over the positive ion fluid, and Q is the charge ratio. So one of the fluids could be chlorine fluid, and the other type of fluid would be a positive oxygen fluid, actually. You see that there would be a certain. Anyway, I'm cutting this long story short, jumping to conclusions. Actually, in the linear regime, since we consider one of the ions represent a beam, actually we have a beam instability, but I will not have the time to elaborate on this aspect. This is a linear instability which can be seen. Moving on to predictions for nonlinear waves, what we have, let me jump over these slides. First of all is a certain modification of the ion sound speed depending on the density ratio between the negative and the positive ions. So keep in mind the positive ions are the dominant, say, ion population. The negative ions will be the secondary ion population. You see that the version of this pseudopotential theory is more complicated algebraically. In this case, you see the parametric dependence on the ratios Q for the charge, zeta, which is the cold electron density over the total electron density, and beta is the temperature ratio of the electrons. So this is becoming already quite complicated. We distinguish different versions actually on the on the existence diagram. The blue curve represents the sound speed as previously. The red curve is when the positive ion density stops to be real, so that's a limit not to be violated, and the green curve is the similar limit for the negative ions. So you see that in the region R1 we can have only positive polarity electric fields. Keep in mind that positive polarity electric fields will be between the blue and the red curve. Negative polarity electric fields will be between the blue and the green curve. So we can have both types in region 2, and region 3 will only have negative polarities. So I think I will not have a lot of time to elaborate on this. What are the highlights of this? I'm jumping fast forward. Is first of all a transition from a regular solitary wave to a super solitary wave that you see here. So working on the topology of the curve, we realize that we have this fishbone space thread, and as a result we get this super solitary waves that we see at the bottom right.
We see a lot of solitary, we see
but again, we see a flutter when we see this flutter between the two pulses actually, which appears numerically, depending again on the topology of the curve. Mathematically, this can be explained. This happens to be, say, instead of having a single root, the potential acquires a double root at some point, and in that case, I mean, this changes the topology of the solitary wave. Again, we can have a situation when we pass through a double layer, which is what we see here. And in the fourth case and last case, again, we see that we could have a double layer situation ending the existence diagram. But in that case, no super solitary waves.
I think my time has run out, so I will try to conclude in the next couple of slides. Actually, these are the variables that we use for Mars observation.
I think my time has run out. So I will try to discover observations for this thing. What is a self-reflective comment on this theory is that obviously this is a very simple theory. In terms of applications, this is too simple. It lacks realism. We have taken both ion types to be cold. We neglected the thermal pressure. We took the electrons to be at equilibrium. And still we seem to get interesting predictions in terms of a polarity reversal. We obtain super solitary waves, flat top solitons, and then we have explicit predictions regarding the dependence on the kappa distribution and on the plasma configuration. I think this is time to say thank you for having listened to my talk, and basically the material presented was based on the publications that you will see highlighted on this slide. I'm happy to answer any questions, although I realize my time may have run out. And in any case, please feel free to contact me by email in case you're interested in this theory. I'm trying to recover, yes, I'm there, to recover the say teams, environment, and thank you. Thank you for listening to this talk. Thank you.
Thank you so much, sir. If there's any question. Okay, there's no question. Thank you so much, sir.
Thank you. Thank you for having me today.
Our next speaker is trying to join, so by that time we can have a very short.
Ladies and gentlemen, while the next speaker joins, we are going to have a 5 to 10 minutes break. Okay? सीधा ही भाई हाँ मेरा ही है एप्पल वाला है एप्पल वाला लोगो डाल देंगे कि कहीं एक्सचेंज ना हो जाए सर पीछे बैठी काम नहीं होगा मैडम सर्टिफिकेट्स तो कम करने के आ गई तो दे पकड़िए आप अब तो आपको रिप्लेस करना है मैं तो कर दी
हाँ? मैडम तो बोली पता नहीं बोली गीतांजलि मैडम सर चेयर है
मैं टेबल हूँ, मेरा सर्टिफिकेट लेके घूम रही हूँ। सारा काम देखो सर, सारा काम मेरा इवैल्यूएशन शीट नहीं, वो लोग लिख रही है, अभी उधर जाना है मुझे।
बच्चा को बुलाइए
आपका काम है, मेरे को पकड़ा रहे हो।
आपका काम था
मेरा नहीं था सर, मैं कहाँ रहूँ बताओ, मैं सर्टिफिकेट लिखूँ कि ये करूँ बताओ।
अरे किसी को भेज दीजिए ना सर्टिफिकेट लिखना है तो सोचते तो खाली उसको बना देना
वो देखने पड़ेगा सर, इवैल्यूएशन शीट में टोटली करके सबको नहीं भेज सकते।
हाँ बात तो सही है अच्छा वो वाला
हाँ, वो साथ में चल रहा है ना।
ये देखिए सत्यरंजन मिश्रा चेयर है
हाँ
चक्रवर्ती सर
गीता अरोड़ा।
दूसरा गीता अरोड़ा ज्वाइन कर चुकी है मैं सर फोन कर दिया हूँ वो 12/5 को ज्वाइन कर लिया बोल दिया अभी थोड़ा ब्रेक चल रहा है आप देखिए 1 2 3 4 बचा है
मैं सर मैं एक यहाँ तक करूँगी, फिर मैं घर जाऊँगी। हाँ घर जाऊँगी, बेटे को लेना है। क्या
अब तो गिरा दिया था फोन हाँ बोल तो रही थी अच्छा
না না আমি বলছি আমাদের স্যার ডক্টর কালকে ডেকে নাটক স্যার
कल
ये देखिए मैडम आप गीता तक कर रही है ना ठीक है ये 3 मैं किसी भी तरह भिखारी की तरह मैनेज कर दूंगा
भिखारी क्यों मैनेज करोगे, अच्छा तो बोलोगे।
किसको मैडम
अरे भगवान, काट तो रहे हैं आप, इधर भी दोगे उधर भी दोगे, कैसे होंगे। एक वापुल सर फोन करो, अभी मुझे को बोला फोन की थी, कहाँ नीचे चले गया उसका नाम।
नंबर सर्च करो ना, बता दो। अच्छा भाई बात
पता है यार तुम, मतलब इतना कॉल सारा देखो मिस हो जा रहा नंबर भी। मैं 2 सर्टिफिकेट गलत कर दी ना।
अरे
अच्छा सर ब्रेक टाइम ওনার টেবিল ক্যান্সেল হয়ে গেছে হ্যাঁ হ্যাঁ অ্যাকচুয়ালি আমাদের ऐसा ना বাড়াবে ওকে বাই
আচ্ছা আচ্ছা এটা আসছে অনলাইনে
না এখন একটা মিটিং আছে যখন জয়েন করতে বলে আমি জয়েন করব
ওকে এখন তো অ্যাকর্ডিং টু শিডিউল ইয়ে রাখা হচ্ছে সন্তোষ লীলা
সম্পূর্ণ সময় ক্যান্সেল আমরা বলছিলাম প্রবলেম
আচ্ছা
হ্যাঁ তাহলে কি হচ্ছে পরে যেগুলো আছে টাইম মেনটেন হবে
ওকে হ্যাঁ তো ডিলেটা ম্যানেজ হয়ে গেল
ইভেন্টটা আমরা দিলাম মাঝখানে সবাই চাপে দিয়ে দিলাম এখন
হ্যাঁ বাস ভালো করেছি
এখন হচ্ছে
ও হেল্প দরকার মানে কিছু
কি না আমাকে এখন প্র্যাকটিস করতে হবে এটা তুমি একটা মিলে করে দিচ্ছি তুমি একটা আমি একটা বাথরুমে যাচ্ছি যাওয়া যাওয়া আসবে
লবিতে আসবে না অ্যাডমিট করে দাও ঠিক আছে ওকে বলছি এগুলো ফেলে দিলে হবে না, কাউকে বলো এগুলো চায়ের কাপ না না
क्या ना वो एडमिट कर रहा है मैं आ रहा हूँ
आप मैथ्स डिपार्टमेंट से आपका नाम हाँ सात जॉइन करছি ଏ ସତ କରୁଛି ତ
हाँ
ସାତ ଜଏନ୍ କରିଛି
अच्छा चलो আস্তে আস্তে প্রথমে ও প্রথমে पहले ईशान मिश्रा से
प्रथमे
हाँ
आई कैन अंडरस्टैंड प्रथमे
हाँ ये ईशान मिश्रा सर उसके
पूरा
बाद
पढ़ना पड़ेगा
हाँ? नहीं आपको जो जो फोटो में लगता था वो बोलना था होमवर्क कर दीजिए
मेरा फोटो आएगा कि नहीं आएगा मैं
आपको
वहाँ पे
फोटो
जाके कहूँ
आपको अंदर में जाकर बोलना
अच्छा वहाँ जाके
पीछे
बोल
जाके एकदम अंदर में ताकि वॉइस इधर उधर ना
कहाँ जाके बोलना है मुझे
वो जो अंदर प्रधान लोग जहाँ बैठते हैं
वहाँ जाना है
हाँ
सीरियसली
हाँ मैं भी जाऊँगा आपके साथ चिंता मत करिए आप अकेला नहीं है ठीक है 12-10 ऑलमोस्ट होने वाला है
ये क्या बात है हम यहाँ पे बैठ के क्यों नहीं बोल सकते
क्योंकि मैडम यहाँ से आवाज आ रहा है ना
और फोटो उठाना
Flash कर
बोलते हुए कहीं ना मेरा नाम है ना फोटो है काम जो है आप करवा रहे हो डेली बुला बुला के
मैं तो
गलत
सुबह
बात
से
है
यहाँ बैठा हूँ मेरा फोटो कहाँ
बहुत
लिया
गलत
मैडम
बात है ए हमारा फोटो लो
हाँ लेकर लेकर मैडम
ए और संपत सर আমার ଗୋଟେ फोटो ले सर कुछ नहीं मेरा फोटो कोई नहीं उठाना नहीं वो यहीं पे बैठे बैठे फोटो उठाएंगे
मैडम अपने प्लीज मेरे ऊपर डाल रहे हैं
रेडी
थैंक यू
सुंदर
ये
दिखना
हमारे
चाहिए
ऑफिस
सर
सर
सुंदर दिखना एकदम
कन्वीनर से थोड़ा फोटो उठाइए
क्योंकि मेरा समय अभी नहीं आया है
थोड़ा आ जाए
आ जाइए फोटो उठाइए काम वाम कर रहे हैं तो एक फोटो रहना चाहिए कि काम कर रहे हैं मिस्टर कुछ नहीं रहे
मैडम बड़ा उठा रहे किसके पास रहेगा पता
ये लास्ट सर मेरे को देंगे मैं आपको दूंगी
स्नेहा सर वाला आपको रेडी है ठीक
थैंक यू हो गया मैं भेज रही हूँ चलो
ये भेजिए
सर वो रूम में आपकी दो लड़कियां बैठी थी ना उनका खत्म होने वाला है हाँ
मैडम नहीं वो बाएं में वो बाएं तरफ छोड़ना वो बाएं तरफ ये डांस
पहले यहाँ पे बोलो बैठने यहाँ पे बोलने से क्या फायदा
एवरीवन सेटल डाउन प्लीज
बैठ जाओ बसन दो स्टार्ट करिए
और हाँ वो तो आप ही को लेना है। Everyone, can you please shift to that side? Please shift to that side. Thank you.
Good afternoon, everyone. For the second technical session of the day, we are running late by some time. Let me introduce to you today's session chair, Professor Satyajan Mishra, who is currently working as Professor, Department of Mathematics, Siksha Anusandhan, deemed to be University Bhubaneswar. He has 19 years of teaching experience in both PG and UG level, and he did his PhD from Siksha Anusandhan in 2013. And since then, he is actively engaged in research work. His area of research is heat transfer, magnetohydrodynamics, porous media, with broad area of fluid dynamics. He has published above 315 papers in international journals of repute, and all are either SCI or Scopus Index. He is having a position in top 2% world scientists by Stanford University, USA, in 4 consecutive years from 2020 to 2023. He has 80 scholars and 6 more students are working under his guidance. Professor Mishra wrote a book entitled Learning Numerical Method Using MATLAB under Bentham Science Publisher UAE, and going to be published very soon. He is also editor and reviewer of many renowned journals of international and national repute. Let's welcome Dr. Mishra for the session chair. Now, I would like to introduce our first speaker of the day, Professor Snehashish Chakrabarti. Professor Chakrabarti has 30 years of experience as a researcher and teacher. Presently, he is working in the Department of Mathematics, National Institute of Technology, Rourkela. Professor Chakrabarti received his PhD from IIT Roorkee in 1993, and his postdoctoral research at the Institute of Sound and Vibration Research, University of Southampton, UK, and at the Faculty of Engineering and Computer Science, Concordia University, Canada. He was also a visiting professor at Concordia and McGill Universities, Canada, during 1997 to 99, and the visiting professor of University of Johannesburg, South Africa, during 2011 to 14. He has co-authored and authored, edited 29 books, and published 404 research papers till date in different international and national journals, and 2 books he is currently writing. Professor Chakrabarti is the chief editor of International Journal of Fuzzy Computation and Modeling, in the Science Publisher, Associate Editors of Computational Methods in Structural Engineering, Frontiers in Built Environment and Curved and Layered Structures, and happens to be the editorial of Springer Nature Applied Sciences. He has many journals journal in which he is acting as editor and reviewers also. He is reviewer of around 50 national and international journals of repute, and he was the president of section of mathematical sciences of Indian Science Congress from 2015 to 16, and he was the vice president of Odisha Mathematical Society. Professor Chakravarti is the recipient of prestigious awards, like Indian National Science Academy nomination under International Collaboration or Bilateral Exchange Program with Czech Republic. Platinum Jubilee, ISCA Lecture Award, CSIR Young Scientist Award in 1997, Voice Cast Fellow, DST UCOST Young Scientist Award 2007 and 8, Golden Jubilee Directors CBRI Award 2001, INSA International Bilateral Exchange Award 2010 to 11, 2015 and 2011 he was selected. Roorkee University Gold Medals 1987 to 98 for his first position in MSc and MPhil. He is listed in 2% World Scientist recently in 2020 and 2021 in Artificial Intelligence and Image Processing category, and based on independent study done by Stanford University scientists. He has already guided several PhD students, and still many more are undergoing research under his guidance. He has hosted around 8 international students with different international national fellowships to work in his group as PDF, PhD, visiting researchers for different periods. Let us welcome Professor Chakravarti for today's session. That's it. Sir, welcome to the session. You can, sir, please start.
So, hello.
Yes, sir, you are audible. Yes, sir.
Yeah, okay. Okay, first of all, thank you for giving me chance to present my talk, and also thank you for this detailed introduction about me. Thank you so much.
So let me share
first my screen, then I will start my talk. Okay. Is it visible?
So actually your slides are not visible.
No.
I can see your screen.
Yeah. Now I will do. My screen is visible now. Yes. Now slides are visible.
Yes, sir. Now they're visible.
1 minute, please. You can see this? Yes?
Yes, sir, they're visible.
Yeah. Okay. So, thank you again, and very good afternoon to all of you. So, as the title goes, it is the computational efficiency of using different step functions in the Rayleigh-Ridge method for solving vibration problems of unsyndicated nanobeams. So, there are a couple of words in this title. Rayleigh-Ridge method is one, different step function is another, vibration problems and unsyndicated nanobeams. So slowly I will light up on all these words, what are those. So as you know, the Rayleigh-Ridge method is a numerical method, and different step function that is used in Rayleigh-Ridge method, when I will discuss about the Rayleigh-Ridge method, then step functions I will discuss. And this is related to vibration problems, although this method can be used for different vibration problems of structures, maybe beams, plates, cells, etc., etc. And here actually we'll use this to the functionally graded nanobeams. So we have functionally graded beams and functionally graded nanobeams. Okay, so with this actually this work is jointly we are working with Akash Kumar Gartia. He is my PhD student. So actually this is his work, but I am presenting. Anyway, thank you. Thanks to my student also. So these are the outlines of my lecture. So first one is literature review, basic concepts, functionally graded nanobeams, Euler-Bernoulli beam theory, Arrhenius non-local elasticity theory, formulation of governing equations, Rayleigh-Ridge method, some numerical measures, conclusion and references. So now I am not going to in the detail of all these work references. So there are plenty of works on these in functionally graded beams and all different theories, and why functionally graded are used, etc., etc. So I'm not going into detail due to the time scarcity. So actually this in actually firstly in 1972 Weber et al. Actually gave the general idea of unsilicated materials for composites and polymer materials. Okay, and this was first applied in means bones, teeth, and bamboo trees, etc. Later in 1987, by Japanese scientists, they used this for excellent resistance against the high thermal flux and at the same time good capability of maintaining structural integrity and safety. Okay, and the historical progress from the pure metal to functionally metal, you can see by the figure 1 is given in reference 9. So this is the actually material development. You see, first we are having this pure metal, then alloys, then surface treatments, power metallurgy, composite metallurgy, and then it comes to FGMs. Fine. So then again there are different development from 2007, 8, 16, 2013, 14. Actually in 18, 16, 8 and 16 and 13, 14, those are our work. Chakravarti, Pradhan and Chakravarti. Then 2013, 2016, 2017. So all these developed different, use these FG nanomemes, okay, to find the vibration characteristics. Then again, if you see 2001, we also used actually this boundary characteristic orthogonal polymers in the Rayleigh-Ridge method. That I am going to again discuss later. So this method, okay. Further, one of my again student Jenna et al. In 2022, he worked on these nano beams with different complicating effects like elastic foundation, non-homogeneity, temperature effect, magnetic effects, etc., and published a series of around 20 papers related to these nano beams. Okay. So now let us come to what is FG beam first. So you see the equation 1 actually here it is having Pz is equal to Pc minus Pm into Z by H plus half whole to the power K plus Pm, where you can see that Z denotes the thickness direction and H is the height of the beam. So if you see the equation 1, Ez is the effective material property at any point and is determine the properties of its two materials. One is ceramic and other one is metal. Okay, so C for ceramic and M for metal. So it is written like such a way this K will control actually these functionally materials, and this is the power law exponent K, which should be non-negative. So actually when you use functionally graded material, so actually there are many advantages. Okay, so maybe electrical and thermal properties of the material also can be controlled. Like suppose some rockets or etc. is going in the space, so you know that when it is going from very high temperature to very low temperature, then sometimes this if you use only the metal or the alumina or whatever, it may crack or it may fail. But if you use the functionally graded, that means it is composite with your ceramic or any other metal with the metal that is rho C and rho M, then it can withstand the temperatures. And you know the Kalpana Chawla that episode, actually there the functionally graded material was not proper to withstand those temperature variation. So that is why these functionally graded structures are very important in application problems. Okay. Fine. So with this, let us come to the next. So this is the actually geometrical view of the power law variation of suppose Young's modulus and density. Left hand side figure gives the variation of Young's modulus for different K. Okay, with respect to Z by H, that is non-dimensional. Z is your Z direction and H is the thickness of the beam. Okay, and Y direction is E. So left side is giving the E set, as you change from K equal to 0 to 10, so you see 0.1, 0.2, 0.5, how these properties are changing. Similarly, right hand side is density. This density again depending upon the K exponent, how it is changing. So this is standard actually for these functionally integrated materials. If you have E and rho like this variation. Fine. So, so I will skip this. Now, coming to this Euler-Bernoulli beam theory, first let us see what is Euler-Bernoulli beam theory. Here, if you see U0, U1 and U2, and this U0 is along x direction, U1 is y, and U2 is z direction. So U0 is expressed as U minus del W by del X. U1 along y-axis is 0 and along z-axis it is W. And remember this U and W, U is the longitudinal displacement and W is the transverse displacement. Okay, so this is equation 2. So now I will go to the nanomaterials with this FGN. So let us see nanomaterials as actually it is, if it is nanometer if you say, so 1 nanometer is 10 to the power minus 9 meters. Okay, so you see it is very tiny actually that we are working on. So there we have used this actually this nano materials or nano beams or whatever, it is being used different directions also, physical, chemical, biological areas. Okay, so because these properties include enhanced reactivity, strength, electrical resistivity, optical behavior, etc. that I told already, and temperature also it can be withstand. Okay. So, if you come now to the equation 3, this is for Euler-Bernoulli beam actually, sorry, non-local beam. Non-local means non-local, this is coming from the nano beam. So, for nano beam, equation 3 gives the constitutive equation. If you see this E0A, that is the left-hand side of the second term of equation 3, this actually controls the non-local part of the nano beam. So, if I put this E0A as 0, that means we don't have nano. So it will be 0. So simply it will be sigma xx is equal to Ez by 1 minus mu square epsilon xx. And this sigma xx and epsilon xx are usual notations where if sigma xx is a stress component and epsilon xx is a strain component, Ez is the Young's modulus and mu is the Poisson system. As those who are working in structural dynamics field or vibration field, they know what are those mu, E, etc. Okay? So now our main target is this E0A, which controls the non-local theory. So with this, now, so these were the equation. Now in the title you have seen the different shape functions in the Rayleigh generator. So shape functions means we suppose the displacement may be longitudinal or transverse as a series of functions. Okay, in the series of functions we will have constants and the functions of x. Okay, along x-axis. Okay, actually x and t anyway. So this constants and x, so these x I can take different functions. Functions means different algebraic polynomials. So here what actually we have done, we have used different shape functions. You can see the first line, different shape functions, that is algebraic, Chebyshev, Legendre and Hermite polynomials. Those are used in the Rayleigh method. Okay, so that is why just all these are all you can see from the books. So algebraic polynomials, just we have given notation as L0, L1, L2, that is 1x, x square, etc. And the state polynomial, that also you know, that is T0, T1, T2, Tn. So different polynomials we have used, and then we try to see that which polynomial gives best result. See, result will be same for whatever polynomial you will use, but which one is computationally efficient. Okay, that we wanted to do with respect to the time of computation. Okay, so Legendre polynomial, this P0 to Pn, then we have Hermite polynomial. So other polynomial also you can use, but we have used only these 4 polynomials. So now come to the functionally gated nanobeam. So if you see figure 3, it shows the typical functionally gated nanobeam. Okay, so along x-axis, that is length L is shown and width is D of the nanobeam and H is the thickness. Okay, so you can see this from figure 3. Now this Ez and ρz we have written in terms of P. Okay, earlier Pz. So here I have written again in terms of E and ρ, that is Young's modulus and density. So it is given by 8 and 9. Okay, where EC, C I already told, C is for ceramic constituent and EM, M is for metal constituent. So E is, that means EC designate Young's modulus of the ceramic constituent, and EM, that is Young's modulus of the metal constituent. Similarly, rho C and rho M are the mass density or density of the ceramic constituent, or ceramic and metal constituent, and K is power law exponent. Okay, so notably we have taken Z as minus h by 2 for the lower surface of the beam in pure metal, and upper surface Z equal to plus h by 2 is entirely ceramic. Okay, so these are the three-dimensional view of those with respect to power law exponent, how it looks like. Okay, for Young's modulus and mass density. Now, this equation also I have shown earlier. So this is Euler-Bernoulli beam theory. Actually, to develop that, we need U0, U1, U2 along x, y, and z direction. So U0 and U2 are non-zero, and U1 is 0. So already it is written where U0 is displacement in the x direction, U1 displacement in the y direction, U2 in the displacement in the z direction, and U already I told is longitudinal displacement, and W is the transverse displacement. Fine. Now, in Euler-Bernoulli beam theory, the strains can be expressed as this, equation 11, where all these stress and strain for different components x, y, y, x, x, z are all 0. And the expression for stress and bending moment and the normal force, etc., are given in equation 12. Right? So all these and these A0, A1, that these are appearing in the previous equation, A0, A1, A2 in equation 12, A0, A1, A2 are given in equation 13. Now if I want to write this strain and kinetic energies are given in equations 14 and 15. So you can see these equations contains the partial derivatives, that means del U by del x, del 2W by del x square, etc. Similarly, kinetic energy T also have the partial derivatives with respect to x and t. Okay. So now the inertial coefficient are defined like this. So as usual for vibration problem, we use Hamilton's principle, where it is 0 to t integral delta s minus delta t dt is 0, we equate it to 0. And the governing equation then we can obtain like this for equation with equation 17 and 18. So further, this equation 19 also I have shown earlier, that is Euler-Bernoulli FG nanobeam. So here you see the second term where it is appearing E0A square. Okay, so this is for nano, that is non-local theory. In that case, the normal force and moment N and M will be revised like this by equation 20. Earlier one was simply pure Euler-Bernoulli FG beam. Okay, so now it is nano beam. So that is why you see in equation 20 again E0A whole square is coming. Okay. So again, we have strain and kinetic energy for these nanobeams. I have S and T, that is S is potential energy, strain energy, and T is kinetic energy, given by equation 21 and 22. Again, partial derivatives are appearing here with respect to X and T, okay, for U and W. Now, you see this equation is having, I told, partial differential equation. That means U and W are function of X and T both. Okay, that means displacement and time. So to get rid of this time, or for simple harmonic notion, actually, we assume that UXT and WXT can be represented as equation 23. But UXT has been written as capital UX into cos omega t, and WXT written as WX into cos omega t. So we'll substitute this in those equations and you will get the vibration equation. That means we will get finally actually eigenvalue problem. So whatever, so S max and T max we will find, and if you see after substituting those two expressions, we will get now the ordinary differentials. Okay, that is dW by dx square, du by dx, like that. Okay, so not del actually removed by that cos omega t for simple harmonic motion. Okay, so now in the Rayleigh's method that I was mentioning earlier, the amplitudes of vibration are now expanded in terms of the following series. Remember, U is the longitudinal vibration, W is the transverse vibration, transverse deflection, sorry. Now, I have this x to the power t into L minus x whole to the power q summation Ci phi I. and the lower equation is Wx, that is for transverse displacement, x to the power p minus all to the power q summation dj psi j. You see the first coefficient in the right hand side for both the equations are same, and you see in the summation I have ci phi I in the first equation, and the second equation I have dj and psi j. So I have constants Ci and Dj. Ci from I equal to 1 to n it depends upon user, and Dj is also j equal to 1 to n. And these phi I and psi j are called step functions. So these phi I psi j, we have taken different polynomials and then substituted in the governing equation and solved. Further, then we saw that we want to see that which step function gives better result, means computationally efficient result. Not better result. Result is same whatever you take, but it depends upon how many n you will take, means what will be the n value or how much time it will take. Maybe n also takes the same value, but maybe time is less for certain step functions. Okay, and this the coefficient in the right hand side, that is x to the power p into L minus x whole to the power q. This is very important. This controls the boundary condition of the beam. Okay, so PQ is having actually values among three, that is 0, 1 or 2. Okay, so if I take P and Q both as 0, that is free boundary condition it will give. If I take P and Q both as 2, then it will give clamped, or like that if it is 1, it is simply simple. It is very simple, and half of the boundary condition actually is satisfied by this. Anyway, sometimes full also, depends upon the problem. So we use these two expressions in our those strain energy, and then Rayleigh method we use, and finally what we will get, see, our main equation now will convert to equation 27, which is nothing but a generalized eigenvalue problem. And we know as a mathematician that we can solve this eigenvalue problem and we can find this lambda. Our target is to find this lambda, which is the frequency parameter. And why I am telling this as generalized eigenvalue problem, this is, you see the left hand side, k minus lambda square m. K is n by n matrix, m is n by n matrix. We know that Ax equal to lambda is, x is the standard eigenvalue problem. Here we have with lambda square also one n by n square matrix. So that is why it is called generalized eigenvalue problem. Fine. Here K is called stiffness matrix, and M is called mass matrix. And it depends, the size of the matrix will depend what value of n you will take. Okay, so if I take suppose n certain value, so accordingly K and M order will change. And similarly, you know that if I have 9 by 9 matrix, suppose, so we will have 9 values of the eigenvalues. Okay, so then we have 9 frequency like that. Okay, so those who are working in vibration, they know this. Anyway, so now for the means special cases or the case studies, we have taken the properties of these means ceramic and metal that we are telling about the FGM, functionally graded. So these properties have been taken from a paper, reference 21. So alumina Al2O3 for the ceramic, E is taken as 380 and rho is taken as 3800. Okay, new Poisson ratio we have taken constant, and aluminium as E70 and rho 2700. And you see the equation 28, this lambda. After those, means there are many simplification, computation, and lengthy expressions are there. I am not showing all those things. So just I have shown you the eigenvalue problem, where those lambda expression is this: omega L square by h into square root m by em, where you see right hand side is appearing omega. And if you remember simple harmonic motion, we have taken cos omega t. What is that omega? That is the natural frequency of the system. Okay, so that is why I never told this lambda is frequency. Lambda is a frequency parameter because it depends upon L, H, rho m and dm. Okay, omega is the frequency, if you say. So, but we are finding lambda because we have non-dimensionalized the equations. So we have this lambda. So if you give different L, different rho m, different em, so you will get the frequency depending upon your what are the C and M, means ceramic or metal. So with this different cases we have solved with respect to rho E naught A by L, that I told that this controls the non-local parameter. Okay, non-locality of the nano beam. So different. Now I'll show the some convergence, means after writing the program of all these things, taking different parameters as I already shown you. that we should first confirm that we are getting the result with convergence, the numerical convergence I am telling. Okay. So if you see now this table, this gives the convergence of first frequency parameters lambda. Okay, for two boundary conditions S, S and CC. So first upper table is for SS, means the beam is having simply supported both ends, and another lower table is CC, that is clamped and clamped. Okay, that means 1 1, that value P I have already shown you, P and Q. So now this n was appearing, summation I equal to 1 to n. Okay, so n we are varying 2 to 8 suppose, and this first frequency means first eigenvalue, that is given by frequency parameter, first frequency parameter. So if you see,
excuse me, sir.
Yes.
Excuse me, sir.
Yes.
Sir, sorry for the interruption. Please try to go over by 5 minutes.
Okay, okay. I'll just I can finish by 2 minutes.
Thank you, sir.
So as we increase n, so lambda is converging, and see time is also there for different polynomials, algebraic, Chebyshev, Legendre, Hermite. Okay. Similarly, CC boundary condition. If you see that algebraic polynomials is taking less time. Okay, that is the main our conclusion actually. So now I will show the tables with different boundary condition and different frequency parameter. That will be the end. Okay. So this is for CS and FF, another two boundary conditions. This is convergency for second frequency, that is second values, second eigenvalue, so SS and CC. This table is for CS and FF. This is again third frequency parameters for SS and CC. This is for CS and FF for the third frequency. So in this way, if you can see all these tables, you can see that I have written here time also. If you can see minutely, then algebraic polynomial takes less time. Okay, so this is better for this particular problem. Okay, if you change the problem, maybe that some other polynomial will give you better result. So in this, what we have found that algebraic polynomial gives better result with respect to time. Okay, and in all the calculations we have taken n equal to 15 to have the confidence that the result will converge. Okay, so with this we have given so again with some special case for K, we have given some comparison also with different LYs, so it is exactly matching with ours. So with this confidence, now these are some new results with respect to L by H, etc. E naught A by L for different boundary conditions. Okay, so for FG beam, so I am skipping this. FF, etc. So these are some plots for first frequency for different E naught A by L with respect to power exponent. Okay, so this is again with respect to power exponent for non-dimensional frequency. This is for first frequency again for different K and different E naught A by L. This is again for power exponent for different values of E naught A by L. This is for variation of frequency pattern with E naught A by L different and K equal to 0.5. Okay. This is for again E naught A by L equal to 0.5. So different means combinations we have taken and played with this model, and we just saw that how the frequency decreasing or increasing, etc., etc. So conclusion, already I told that different step functions have been used in this important problem of functionally getting nano beams using Narrell-Digge method, and we conclude that the algebraic polynomial for this problem gives best result with respect to time. So with this, so these are some references. So these are some references. So these are some related publications from my research group by my students. Okay, so there are other papers also we have not included. These are some our papers. So these are 4 or 5 books that we have written, and again with my PhD students. So first one is vibration of plates. Long back I had written, single author anyway. So then vibration of functionally beams and plates with my PhD student Karan Kumar Pradhan. So here you get functionally materials for beams and plates vibrations. So left side again nano beams and nano plates, static and dynamic problems with Lakshmi Bera, again my student I wrote with World Scientific Publications. Right hand side again with Karan Kumar Pradhan, computational structural mechanics, static and dynamic problems from Elsevier. And with this, these are my research work you can explore by scanning this. Okay. So anyway, thank you so much. If you have some problem, some question or any suggestion or any query, so you can ask. Okay. So I am now stopping sharing. No problem. Or you want to ask something? Hello?
Yes, sir, no problem.
Okay, so
You can
I'm
stop
stopping.
sharing.
Okay.
If anyone has any question, can ask. Else, we can proceed. Thank you, sir, for the nice session. It was wonderful listening to you.
Thank you so much. Thank you so much.
Thank you,
Okay.
sir.
So I can leave now?
Sir, thank you.
Okay. Thank you. So I'm leaving, please. Thank you so much. Okay.
Thank you, sir. So let's proceed with our next speaker. Next speaker is Dr. Geeta Arora ma'am, who has earned her PhD degree from IIT Roorkee in 2011. She is working as a professor in Department of Mathematics at Lovely Professional University, Punjab. She has over 12 years of teaching experience and published around 60 research papers in both international and national journals. She has authored 15 book chapters in national and international publications. Also, she has written a book on Vedic mathematics and a book on essential statistics. She has also edited a book on numerical methods in Taylor Francis and is currently working on books with Elsevier, AP Taylor Francis, and IGL Global. Her area of research is the development of numerical methods and statistics. She received the Research Appreciation Award in 2017 and 2019 from Lovely Professional University, Punjab. She has conducted several workshops on MATLAB and Vedic mathematics for students and faculty members within and outside the university campus. She has supervised 8 PhD scholars and is currently guiding 4 PhD scholars. Let's welcome Dr. Geeta Arora ma'am for her speech. Ma'am, you can please proceed.
Thank you, ma'am. Ma'am, is my screen visible?
Yes, ma'am, it's visible.
So let us start with the talk. And thank you so much for giving me the speakers. Like as I have seen, that there are speakers from the different areas of mathematics. So here we are going to discuss about a numerical method, a differential partition method, in which we are using the B-spline, and we are making it as a hybrid with the optimization technique. So let's start with this. Myself, Dr. Geeta.
Ma'am, excuse me, ma'am.
Ma'am.
Excuse me, ma'am. Ma'am, can you do that full screen?
Full screen. Is it not coming on the whole?
No, it's not coming as full screen, ma'am.
Let me reshare it. Can now see? Is it visible?
Yes, ma'am. Now it's full screen. Thank you, ma'am.
So let's start. Myself, Dr. Geeta Arora, Professor at the Department of Mathematics in Lovely Professional University, and I'm working with the numerical methods, and in which I'm working with the differential quadrature method with B-spline as a basis function. And right now we are working with the optimization technique, that is a hybrid one, to find out the results. So let's start with the outlines. That here in this talk I will see how we can start with the numerical methods, what is the importance of the differential quadrature method, and how we are using the optimization techniques. I hope so that the user will be benefited with these. As a whole, if I talk about what I'm going to cover is, so we are going to talk about the differential quadrature method, which is an efficient method solve the complex problem. We are enhancing the differential quadrature by incorporating the B-spline basis functions, and what novelty we are doing in our work, because B-spline and differential quadrature methods are not new. What novelty we are looking for is we are involving the optimization technique, which is a hybrid technique we can say we have developed, and it is just right now we are working on it. So I thought that this is the research that I can give it in this talk. So let us start with this. And in order to start with it, let's first see that what is the requirement of the numerical methods when already we have a number of equations which are already being solved by the analytical method. So the first point of view is that numerical methods are always coming as a savior when we are solving some of the complex problems. And right now in this advancement of technology, with this all the softwares coming handy to us, we know how to use a mathematical software. So solving a problem which is a mathematical problem, either a differential equation which is a partial one or involving non-linearity, if you are looking for the mathematical solution to be obtained, there is no need of a pen and paper. Directly we can use a software you can program it. And especially the numerical methods. With analytical methods, obviously you have to do a lot of work. So the beauty of numerical method is that we are creating the programs, we are using them as such, and we can solve the sort of problems. And if we talk about the already well-known numerical approaches, so these are the finite difference and finite element methods, which are obviously known to all of us. But the thing is that still we are developing the new approaches. We are looking for the new concepts to be explored, that how these methods can be made efficient, how the things can be improved. And this is what we are looking for as a research. So right now we are working with the differential quadrature method. Let me tell you what it is and how old it is. We are doing the research with the differential quadrature method, but it is a very old method being developed in 1970s, and it is a competitor of the techniques like finite difference or finite element method. What the difference is, finite difference and finite method, finite element methods are itself, you can say, very well equipped. If I am using the finite difference method, there is no need of any other tool. But what differential quadrature method is, it is just that we are, you can say, we are finding out the derivatives, we are approximating the derivatives in a way that I need a basis function, and here basis function makes a particular rule that how much efficient that basis function along with the equivalence. Right? And what the advantage or the requirement of this method is that whatever we are doing with other finite difference method, we have to look for the solutions when it comes to nonlinearity, or when we are solving a higher order differential equations. That are very clear. But when we are talking about the differential quadrature method, so a very high complex method or the higher order differential equation having a number of nonlinear functions can be easily solved with this method. So this is the beauty of this method, that we can handle, because what we are doing, if I just go into the essence, we are converting whatever the system of PDE I am solving to the ODE using this technique. And then would be is doing the solution using any of the known methods. So that is the beauty. Now we talked about here, I have just explored because the time is very limited. Here we are talking about that what we are actually doing. So in differential quadrature method, we are finding out the derivatives whichever are working in the PDE to be solved, and how we are converting in it for the approximity. We are writing it out as the approximation of derivative with the linear sum of the function itself. Here you can see. I have shown here four derivatives. I use a function with respect to x. I can write down summation of aij's into uxj. Uxx is equal to summation of bij's into uxj. So what is uxi's are? They are the function itself. We are approximating the first order, second order derivatives with help of these unknowns, such as aij's and bij's to be obtained. And these weighing coefficients, we call them as weighing coefficient. So these weighing coefficients need to be calculated with help of a basis function. Here I am using only B-spline basis function, but because I believe literature, you can see that a number of basis functions are there that has been used with the differential quadrature. So depending upon the basis function, we can approximate the derivatives and hence find out the methods to be solved to find out the unknowns. So here we are talking about that I am using the B-spline method. So this is the tridiagonal method. Which and here the whole detail can be done. So it's very simple that if I want to explore, I'm getting this matrix for how to obtain the weighing coefficient, just we need to open. This is a whole with I goes for 1 to n and k going from 1 to n. And once I will get all this for the first not bit, I will get a metric system like this, and this will be done for all the node points. Means once I am solving a problem in a particular domain. So for that whole domain, I need the number of metric system to be obtained. And as I'm saying, the programming is very easy. So we can expect that just I'm creating a program that will take the first, you can say, the domain what, and finding out the solution at that. Then we are finding out the second metric system at the second point. So a number of metric systems need to be created. But since it is all, you can say, if I talk about this, if I talk about this metric 61041, it's at the right hand side, which here I have shown for the first one. It is going to give me a pattern. So once we are getting this metric system and exploring it for the other numbers, we will be able to get the weighing coefficients. Once I have the weighing coefficients as AII, then using this, it is actually a relation between AIJs and VIJs. So using this relation, I can find out VIJs, and if I show you back, but our VIJs, we have seen that AIJs are the weighing coefficient to be used in the first order derivative approximation, and VIJs are coming from the second order or are required at the second order approximations. So using this, I can approximate the first order derivative, the second order derivative, and similarly, there are higher order derivatives. I can calculate them from this relation. Right, so here it all depends upon the basis function I have employed. So this is what the things are. Now here what it is, a number of B-splines can be used. Means if I talk about B-spline, is the standard B-spline we are talking about. But if we talk about the B-spline, they have some different properties like local support, partition affinity, smoothness, means whatever a basis function has. But there are the different forms of B-spline in which there is some lagging. Lagging means if we talk about the form of exponential B-spline, so here we are getting the exponential function into the basis, and along with the formulation, there is a parameter that needs to be calculated, and without it, I can't implement. Similarly, if I talk about trigonometric B-spline, so trigonometric B-spline has sine and cos because it shows the trigonometric functions and it helps in the periodicity and continuity of the function. So here I have shown the exponential B-spline. From here you can see I'm getting the exponential being involved, and all the values on this function I've given this, say the substitutions I have with for alpha 1, beta 1, whatever the values are in this concise. But what the thing is, I have all the values. I can calculate the basis function value at each and every domain partition, but I don't have the value of W, because it is a parameter which is being taken in literature as an arbitrary value. So in order to deal with this arbitrary value, what we are doing is we are using the optimization technique. Is I can solve a problem using differential quadrature method and the B-spline when that particular parameter is known to me. Until now in literature, people have used an arbitrary random value. What we have done is, we have said that why to take any random value, let's make it efficient. Let's find out which value of the parameter will give me the better solution. And for that purpose, we are using particles from optimization technique. Now, what a particles from optimization is, it is an optimization technique based on the find out their food. But here we are using mathematics to find out the optimum solution in a given space. You can write about the optimization technique and might be aware of, and this is what the layout of PSO is. That here we are using the particle based, means whatever the particles are, we are choosing their particle based values. From each of the best value of the particles we obtain, we are finding out the global best particle value. We are looking for the criteria. According to which criteria we are going to stop it. If we are getting it, then the procedure will stop. If I am not getting the required value, then I will increase the iteration. I will update the velocity of particle, and again I will do the same process. This is what is inside the PSO, how this works. And if I talk about, if you want to explore more about PSO, you can look for very good videos available on YouTube regarding Yapi's visual. You can see that what a PSO is. Here I have just given a brief layout. And here if we talk about how we are doing, so we are saying that first we will initialize the PSO algorithm and given the range of the unknown parameters which is required, The second step is with all the algorithm in which the differential quadrature method along with the exponential B-spline function is being used. Means I'm solving a differential equation of PDE with differential quadrature method and exponential B-spline basis function. But as I quote that in exponential B-spline function, there is a parameter which is missing, which needs to be calculated, that of which parameter value I will get a correct value or the accurate value, right? Here accuracy means I will find out the errors between the numerical values and the single values. Now, what are the known values means if somebody has solved the given differential equation with the analytical method and they are saying that this much accurate our method is. So in order to find out how much accurate our scheme is, we are comparing our solution with their solution. Or we can find out the PD is equal, can find out the exact solution, and then we'll find out that for which parameter value I'm getting the minimum value. Right? And RM is I'm talking about the L2 and in infinity RM. Once we have done with all the calculation is what we are doing, the whole range is divided. Let us say I'm giving a parameter value should lie between 1 to 10. So what PSO will do, PSO will divide this 1 to 10 in the number of partitions. For each particular value of the parameter, the whole code will be running. Once the code is running, it will give the errors, and it will be done on the back end from all the values like between 1 to 10. Let us say I have divided the whole domain into 50 points. So for all 50 points at the back end, the optimization will work. Once I'm getting that which of the following is giving us the minimum error, so that is being kept at the first iteration. Similarly, we are going to have the next iteration finding for the value. But our man will be enough solution. So this is what we are saying that the third step is about value of errors are used to as objective find out that if it is okay, it is fine. Otherwise, will being false. So yes, so move to the next step. Here I have taken just a very simple example that if we talk about how to implement it. So here I have taken a Berger equation, which is a well-known equation, and here the mu is representing the coefficient of viscosity, which is greater than 0. Alpha is a positive constant, and it actually resembles the Navier-Stokes equation in the one dimension. Now, in order to find out that how much efficient our method is, we are saying that let us solve this equation in a particular domain 0 to 2 with zero boundary condition and initial condition taken from the exact solution for this alpha as 1. Means right now we are taking this driving force as 1 so that it will be simple to solve. And for the different values of y2, so what I will do, I will approximate this zx and zx as the differential quadrature approximation I have shown you. And once I have substituted the value of the derivatives, I can see that these are the numerical values I have obtained. So actually, the PDE will be converted into an ODE. And for that particular ODE, I can find out the solution using any of the method. Here we have implemented the RT method, Ruby-Kutta method. And what is now the role of PSO is that when I will start with the whole algorithm, I do not have a particular value of the parameter. So in order to initiate, I will take a value in a domain. Let us say that the value of parameter is going from 1 to 10. I will observe where the values are going, and if I am getting the better value at one side, then slowly and steadily I will increase the minimum and maximum for that particular given parameter. And here if I show you what the results we have obtained, so you can see that for t is equal to 0.1 or 0.1 time level for the different values of mu, these are the results we have obtained, and the results are coming for the parameter we have denoted here as p for the easiness to understand. It's omega in the exponential B-spline function. So we are saying that that we got these values as an errors for 200 and 150 value, and we have shown the comparison also. So how we come to know? Because otherwise in literature the random value is either just taken as 0, 1, 2, very small values they have taken. Now what we are showing is that if I'm using exponential P-span function, it is not necessary that you can get the better result for any random value. But in order to get a specific value with the minimum value, I can use some optimization. And here I have compared the results that is being reported in literature using the finite difference method. You can say the results are almost similar. Right, 4.62, we are getting 4.2 when the parameter is 200. I got the value which is 3.33, 3.8. You can see it's very good as compared to, or you can say better as compared to this. And it actually matters. Means you can say it's 4.62 and I'm getting 4.002. It's with the same errors, e raised to power minus 11. But this is what matters in numerical, that how much good our method is if I compare the errors. So you can see the errors are for L infinity we are getting good, for L2 it is approximately same. Right? And similarly with the standard B spline I have compared, how much is the result being shown in the literature and what we are getting. And one more thing which is very good in the differential partition method as compared to the finite differences, that here we are getting the result for very small step size. You can say I've taken 0.1. This is also for my paper 0.1. It means the whole domain is, if I take 0 to 10, it is being divided into 10 parts, right? Whatever the domain here, I think I have taken 0 to 2, right? So here I have divided the whole domain into 10 parts. So it is coming as this. And for the finite difference, 0.025. Similarly, here we have shown the result that the same results and the behavior of the results are same when time approaches at t is equal to 1 or different values are new, and these are values parameter that is being given from the PSR. Here I have shown that what are the results that I can see, that how much is the numerical and the analytical results matching. You can see here we have two things. It is being shown as a numerical and the analytical solution map. The same thing is being shown as a behavior on the 3D plots using MATLAB, that how we can say what is the behavior of this equation when the time approaches from 0.1 to 1. So these are the behavior of the solution at t is equal to 1 for a particular value of mu. These are the references for the budget equation, that whoever has done the work for the ratio quadrature method for the particle sum optimization. And recently we are working with the optimization techniques. So these are the current work that I can show you, where you can explore the particle sum optimization and how we are using the exponential modified cubic spline in the differential quadrature. Thank you so much. If you want to contact me, this is where my details. Thank you.
Do you have any questions? Are there any questions for now?
If any question are there, I'm happy to take it.
Okay, ma'am, it seems. Thank you, ma'am, for the session.
Thank you so much.
Wonderful listening to you, ma'am. Thank you. Now there will be a lunch break from 1:15 to 2:15. The next technical session starts sharp at 2:15. We can go upstairs for the lunch.
मिताली मैडम
देखिए
यहाँ पे दिख रहा है, यहाँ पे दिख रहा है।
हाँ नहीं यहाँ पे ମାନେ ତମର ପୂର୍ଣ୍ଣ ଇଏ ଅଛି କି କଣ କହିଲ ଲିମିଟ ଅଛି ତମେ ଏବେ ଫ୍ରି ଅଛ କି ନାଇଁ? ତିନିଟା ତମର ଟାଇମିଂ ଥିବ ନା? ଆଚ୍ଛା ହଁ ହଁ ଆଚ୍ଛା ହଉ ସେଡ୍ୟୁଲଟା ଆସିଯିବ ବୋଲି ମୁଁ ଶୁଣିଥିଲି। ପୁରୀ ଯାଉଛ କଣ ହେଲେ ଇଏ ପ୍ରେଜେଣ୍ଟେସନ ଯଦି ନଦବ ତାହେଲେ ତମର କ୍ୟାନସଲ ହବ। ସାର୍ କଣ କହୁଛ? ପୁରୀ ଫୁରୀ ବନ୍ଦ କର, ଏବେ ରହିବ ଯଦି ରୁହ, ଏଠି କାମ କର। ଏବେ ଅଛି ମାନେ ମୁଁ ଟାଇମିଂ ଟା କହୁଛି 4ଟା ବେଳେ ପାଖାପାଖି ଅଛି। ହଁ सर स्टूडेंट अभी आया है मैं बोल रही थी इसको मैं उस डेस्कटॉप पे लगा दूं मुझे कुछ इंस्ट्रूमेंट्स आपको जो कैमरा का ऑप्शन आएगा वहाँ आपको स्पेस लेता है W300 का नाम इसका। अरे वो कब है वो इसको जब मैं ऑन करूँ तभी है बाय डिफॉल्ट तो सिस्टम का जो कैमरा है वो तो ऑटोमेटिकली है ना एक्सेप्टेड ना आप जानते हैं आप इनबिल्ट कैमरा नहीं नहीं हाँ मैं तो डेस्कटॉप में करूँ कैमरा है तो फिर मुझे हाँ मैं वो क्वालिटी हाँ नहीं इसमें तो फर्स्ट we'll refer the normal our text about the CL तो but we'll refer the first one में
वो कितने बजे है?
स्टार्ट हो जाएगा उन लोगों का 3 बजे।
हाँ
उनका रेडी कर लूंगा।
ओह अच्छा अच्छा, हाँ 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 ठीक है। यहाँ पे तो जैसे चलता रहेगा।
यहाँ पे चल नहीं पाए।
अच्छा
क्या करना होगा?
हाँ
यहाँ मैं लंच में कुछ
हाँ ठीक है।
ठीक है।
हाँ
आपकी वाला कितने बजे से स्टार्ट होगा?
2:15 तो बोला था, 20-25 तो हो जाएगा।
कम लगा।
हाँ वही। देखिए ऐसे भी हम लोग का जल्दी खत्म हो जाएगा ये। देखिए सॉरी, ये देखिए शेड्यूल, ये कैंसिल है, ठीक है। तो ये जो है सचिन शॉ, ये इनके जगह आएंगे 2:15 to 2:45, और ये जो है अपोलो मुजम्दर इनके जगह आएंगे। तो हम लोग का 3:20 तक खत्म हो जाएगा।
3:20
साढ़े
तक,
तीन
ठीक है। उसके बाद अच्छा आपका भी ऑनलाइन सेशन है क्या?
नहीं मेरा नहीं है, मेरा
आज
यही
4
है।
लोगों का है आज। मुझे बताइए कौन कौन है, ताकि उनको अभी बिठाना है। ऑफलाइन वालों को तो चाहिए।
26 का ऑनलाइन। बैठ जाइए बैठ जाइए।
हम गिर सकते हैं पेपर से, अभी नहीं जी। अभी उन लोगों को बिठाऊंगा उनके जगह, उसके बाद स्टार्ट करूंगा। बता दूंगा कि ऐसे ऐसे करना है। अभी से 4 लोग हैं जैसा मुझे पता है।
हाँ एक है अर्जुन पॉल, मानस कुमार मोहंती, अर्जुन। हाँ एक है आशीष,
मैडम
एक है
स्वीट
वर्षा,
मैडम।
एक है स्वीट। आशीष, अर्जुन, वर्षा, स्वीट करके
चारों को अभी
खत्म।
मैं मैसेज करता हूँ।
25 और 26
ग्रुप में कर लेता हूँ। कल्चरल इवेंट्स यहाँ पे होगा?
कल्चर मुझे एग्जैक्ट पता नहीं कहाँ पे होगा। वो कहाँ पे होगा ना, यही है क्या? इतना छोटा स्पेस में तो नहीं होगा।
कुछ थोड़ी। हाँ वासुदेव रोड कैंपस 1 बीजीए लिखा है 1 2। हाँ 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 ना,
बोलो बोलो।
पढ़ाई देंगे आप
ना मैं तो आपको इसको मोटिवेट करने के लिए बोला है। बोलो।
निकले सिस्टम चाहिए। हाँ वहाँ पे चलता है ना। मैं अभी ये कॉन्फ्रेंस हॉल वाला क्यों ऐसे ब्लैंक दिखा रहा है? अच्छा हाँ उसका ये स्क्रीनशॉट है ना इसलिए। और ये वो भी ऑफ कर
वो तो
दिया।
कैमरा ऑफ है इसलिए।
थोड़ा वेट करो। दिखाई दे रहा है?
हाँ हाँ
वहाँ पे सर्वर
अच्छा यहाँ पे ना, यहाँ पे लंच ब्रेक ही है। अच्छा ठीक, कुछ चेंज होगा तो बोल दूंगा। समझ रहा हूँ, समझ रहा हूँ। नहीं यहाँ पे लंच ब्रेक ही है। कर्सर कभी कभी हिल रहा है। मतलब स्क्रीन फिक्स्ड है, कर्सर हिल रहा है।
बस वो ग्रुप ही चाहिए।
और तब ठीक है।
जा रहा था क्या?
ना एक बार भी नहीं गया, एक बार भी नहीं गया।
अच्छा इंसान है।
जब तक डिस्टर्ब नहीं कर रहा हूँ तब तक ठीक है। उदय मैडम तो खाना वाना खा रहा था, फिर पता नहीं कहाँ चला गया। बोला तो था यहाँ पे आने।
जाती होगी और नीचे
नहीं, ये तो स्पीकर्स का इंट्रोडक्शन, ब्रीफ बायो।
सर कहाँ पे हैं आप? सर मैं आ रही हूँ आपके पास, 2 रजिस्ट्रेशन के लिए कैसे हैं?
क्या है? राज्योती उनका टी टाइप है।
टी टाइप
लगा ना? मैं लगाऊंगा, अब तक फिलहाल आप लगा दीजिए। हो रहा है ना? ठीक, कोई दिक्कत नहीं है। अरे ये तो काला हो गया। हाँ लंच ब्रेक, अप्लाइड मैथमेटिक्स, हाँ बैनर बैनर, हाँ कल्चरल वाला, हाँ उसको शेयर कर दीजिए। एकदम सही है। आई अभी थोड़ा स्लो है लेकिन हो रहा है। यही आ रहा है, यही आ रहा है। थोड़ा स्टार्ट होने के बाद जाएंगे क्या? स्टार्ट होने के बाद जाइए।
वो स्टार्ट होगा
तो 2:30 मैक्सिमम।
बस उन लोगों को बता के आऊंगा 10-15 मिनट। लोग तो आए नहीं ना, और वो बड़े बड़े लोग भी तो आएंगे।
कब आएंगे?
हम स्टार्ट कर लेंगे तो
जल्दी आइए, जल्दी आइए। हाँ
देख लीजिए कंप्लीट प्रिंट आउट
किसका? स्कैन बिलो टू वॉच लाइव सेशन। ठीक है, सही है।
जल्दा नहीं तो खोल देना सिस्टम अभी वैसे रखो करूँ 25 उसके बाद उनका सिस्टम का पासवर्ड है 1050 ठीक है मुझे कॉल करना और वहाँ पे पानी दे रुक जाओ कॉल कर रहा है
जो पढ़ाने पढ़ा।
मेरे मीटिंग पढ़ पाएंगे?
नहीं सर,
हाँ
ये पहले है क्या? ये पहले वाले है?
हाँ,
डोंट टेल मी।
ये सेशन चेयर है राम प्रकाश शर्मा। उमा
He is currently appointed as an associate professor at the Department of Mathematics and Statistical Sciences, College of Science, Botswana International University of Science and Technology. He pursued his PhD from IIT Kharagpur in mathematics. He also did his postdoctoral studies at the University of KwaZulu. KwaZulu-Natal, South Africa. He has published more than 125 research articles in SCI, SCIE, Scopus in the journal. He also has 3 books and book chapters. He also has few book and book chapters and 7 conference proceedings and several conference presentations. His research areas include diverse topics such as solute dispersion phenomena, magnetic drug targeting, heat and mass transfer analysis, fractional blood flow modeling, and mathematical modeling on climate change. He received research grant from Botswana International University of Science as well as CSIR India. He has given expert talks as invited keynote and guest speaker in several conferences international. He serves as life member of several reputed organizations such as Indian Society, Indian Society of Theoretical and Applied Mechanics, Calcutta, Institute of Theoretical Physics, Indian Science Congress, and South African Mathematical Society. All that being said, I welcome you, Dr. Sachin, to start the session. Khatam. Inka. Chair. Professor Dr. Ram Prashad
obtained his
ये पढ़ना पड़ेगा डिग्रीज सीधे पीएचडी से चलते हैं काट दीजिए लंबा करो was awarded the PhD by the Department of Mathematics, University of Rajasthan. Dr. Sharma is currently working as member of Board of Governors, Senate Dean Administration, and Professor of Mathematics at the Department of Mechanical Engineering, NIT AP. He has more than 32 years of UG and PG teaching and research experience. He has supervised number क्यों बोला सर? He has supervised many PhD and MTech students and 15 BTech students for their project work. Currently, 10 students pursuing PhD and 6 BTech students pursuing their PhD on their supervision. Exactly, covers his research work, research area. Area covers boundary flows, material flows, heat and mass transfer flows, non-porous, nanofluid flow problems, and many other. 215 था
215 तो बोला था, लेकिन सर कैमरा तो ऑन नहीं कर सकते, कैमरा तो ऑन नहीं कर सकते।
अरे कैमरा मैन कहाँ गया? उनको आसर से मंगवा दूँ बरसों ना दे।
मेरे फोन पे
ଖାଇବା ପାଖରେ ଆଉ କିଏ ଅଛନ୍ତି କି ସେ ସବୁ?
कैमरामैन है
हाँ
सर क्या कैमरामैन को ढूंढने जा रहे हैं?
नहीं, बुलाने जा रहे ऊपर से। ये इवैल्यूएशन शीट और वो जो हमने कैलकुलेट किया था बेस्ट पेपर अवार्ड के लिए। अच्छा इसका हाईएस्ट तो कॉमन करेंगे ना, इसीलिए तो ये जो अभी रखेंगे एंड टुमारो हम ये बैठ के पूरा फाइनल करेंगे।
हाँ वही वही
ये डे 1 है।
हाँ
ठीक है
बोले सर आ जाइए तो बाद में करेंगे सर आ जाइए स्टार्ट करेंगे सचिन सर ज्वाइन कर लिया है हाँ स्पीकर जो वो ज्वाइन कर लिया है कोई बात नहीं आप हाँ करके आइए ठीक उसको यूट्यूब लिंक ऑन करना है ना आ रहा है वो बोला 2 मिनट के अंदर आएगा हाँ कहाँ जाएंगे अच्छा आपको जाना है ना तो
नहीं मैं हूँ 2 मिनट में है तो मैं हूँ हाँ 2 मिनट में आएंगे तो मैं
बस 2 ही
मैं 2:45 इज माई एक्सट्रीम मतलब खींच के
समझ रहा हूँ
उसका बस पहुंचेगा 2:55 मैं पहुंचूंगी 2:55 ओके अदरवाइज ये ऐसा कि वो खोल के अंदर भी नहीं जाएगा ऐसे ही बैठेगा उसको डर लगता है
कितना बड़ा है
10 years 10 हुआ नहीं है 10 होगा
अच्छा
सितंबर
है फिर
हाँ
तीन
बट
हुआ है
ही
मतलब
इज
3 4
टॉकिंग लाइक आएगा शाम को देखेंगे
क्या क्लास 3 4
5
5 ना
ही शुड बी इन 4 बट ही इज इन 5
एक्सपर्ट बच्चा
एक्सपर्ट नहीं है वो पापा's फॉल्ट
क्यों
जब वो 2.5-3 साल का था वो जस्ट वो प्ले स्कूल में छोड़ा था, वहाँ पे एलकेजी खत्म हो गया। तो मैं जब प्रॉपर स्कूल में ली तो आई थॉट कि फिर से एलकेजी रिपीट होगा। हिज फादर फाइटेड, क्यों रिपीट करेगा मेरा बेटा ये सब। एवरीवन इज सेइंग कि एज नहीं हुआ है,
जितना पॉसिबल हो कम करना है,
कम
ज्यादा नहीं
करना
करना है।
हाँ
बाद में फ्रस्ट्रेशन ना हो।
हो रहा है अभी, इसको बोल रहा है सब कोई पढ़ रहा है, एवरीवन नोज एवरीथिंग, आई डोंट नो। बट ऐसे बाहर का बाकी चीज में टच हूँ।
हाँ ठीक।
सशु कहाँ गया है?
फोन कर रहा हूँ।
एवरीवन इज वेटिंग। सेशन चेयर कहाँ है? सलमा शेर।
वो अपना ही है क्या?
नहीं हूँ, मतलब जानते हैं हम,
अच्छा।
पुराने जान। शर्मा सर कौन? अरे शर्मा सर खाई सारे टिके तौक आना तो सेशन चेयर इंट्रोडक्शन दे दिए तापर पड़े जाए। सब अपना सांठ गांठ बना रहे हैं, कभी रेणु मैडम, कभी ये कभी वो।
है कौन शर्मा सर?
वो NIT अरुणाचल प्रदेश।
अपन को कैसे?
वो सत्यरंजन सर के क्लोज फ्रेंड है, तो उनका बेटा को मैं पढ़ाती हूँ, तो यहीं पे पढ़ता है।
ओ स्वामी
नालायक। अगर अच्छा है दिखने में तो उसका काम है बस लड़कियाँ।
लड़कियों को पीछे घूमना।
तो लड़कियों के पीछे बैठता है, पढ़ाई नहीं करता है। अरे पढ़ ले शर्मा, पढ़ ले, कहाँ पढ़ेगा, सो जाता है क्लास में। अभी पापा आए तो बोल आगे सर चलो।
आ गया
आयुष नहीं है, शर्मा सर आगे चलो, शुरू करते हैं। वहाँ के ऑन
यूट्यूब ऑन नहीं हो रहा ना?
कैसे ऑन होगा? उसको पूछो ना, बोलो सब वेट कर रहे हैं सर, पूछ लो और हम कर लेते हैं। चैनल चेंज तो प्रिंटर और अभी वो है ऑनलाइन Good afternoon, everyone. Welcome back to the third technical session of the day. We have two talks right now lined up, and it will be session will be chaired by Professor Sharma. Professor Sharma has PhD in fluid dynamics by the Department of Mathematics, University of Rajasthan. Dr. Sharma is working as member of Board of Governors, Senate, Dean, Administration, and Professor of Mathematics at the Department of Mechanical Engineering, NIT Arunachal Pradesh. Professor Sharma has more than 32 years of UG and PG teaching and research experience. He has supervised 4 PhD degree, 5 MTech students, and 15 BTech students for their project work, and there are currently 10 students pursuing PhD and 6 BTech students are pursuing their project work under his supervision. He is actively engaged in research in field of fluid mechanics. His research area covers boundary layer flows, Newtonian and non-Newtonian fluids, heat and mass transfer in porous, non-porous media, nanofluid, flow problems, and many others. Dr. Sharma has published more than 100 publications in peer-reviewed national and international journals. He is also a reviewer of many reputed national and international journals. He is a life member of more than 1.5 dozen national and international academic societies. Dr. Sharma was elected Joint Secretary of the Executive Committee of International Society for Theoretical and Applied Mechanics, IIT Kharagpur, for a tenure of 3 years, and elected member of Executive Committee of ISTM from December 2014 for a tenure of 3 years. Dr. Sharma organized several national and international conferences, and as well as some popular lecture series, one IST on lecture linear algebra, one teacher's enrichment workshop on partial differential equation, sponsored by National Center of Mathematics, IIT Mumbai. Dr. Sharma has participated in more than 200 national and international seminars and conferences, and also has presented research papers there. Dr. Sharma has given many invited lectures, acted as session chair, and attended over 15 ATM workshop and summer school and induction programs. Welcome to the conference, sir. Now let us get introduced to our first speaker of the day, Dr. Sachin Shaw. Dr. Shaw is currently appointed as an associate professor at the Department of Mathematics and Statistical Sciences, College of Science, Botswana International University of Science and Technology. He pursued his PhD from IIT Kharagpur in mathematics. He also did his postdoctoral studies at the University of KwaZulu-Natal, South Africa. He has published more than 125 research articles in SCIE, Scopus Index journals. He has 3 books and book chapters, 7 conference proceedings, and several conference presentations. His research areas include diverse topics such as solute dispersion phenomena, magnetic drug targeting, heat and mass transfer analysis, fractional blood flow modeling, and mathematical modeling on climate change. He has received research grants from Botswana International University of Science and Technology as well as CSIR India. He has given expert talks as invited keynote and guest speaker in several conferences and webinars. He also served as life member of several reputed organizations such as Indian Mathematical Society, Indian Society of Theoretical and Applied Mechanics, Calcutta, Institute of Theoretical Physics, Indian Science Congress, and South African Mathematical Society. All that being said, I welcome you, Dr. Sachin, to start this session.
Good afternoon, everyone. Let first I try to share the slide. First of all, thank you to the organizing committee to give me the opportunity to present my work. Let me see if is the presentation is visible.
Yes, sir, it is visible.
Okay. Thank you for the nice introduction. And thank you to the organizing committee to give me the opportunity. If you see, the topic is here, heat transfer analysis on hybrid nanofluid flow over sphere with interfacial nanolayer mechanism. Generally, we are familiar with this nanofluid concept, which start with the concept of nanoparticles. Nanoparticles has the size generally from 1 to 100 nanometer, and it has we can see different shape it has, and also different metallic and metallic oxide are using as a part of these nanoparticles. These nanoparticles has several applications because they have their different thermophysical properties. So based on these thermophysical properties, it has applied in different field of industries, like that in paints, agriculture, biosensor, medicines, drug delivery, automobiles, those things. And these nanoparticles, when we are immersed in some base fluid, it may be Newtonian or non-Newtonian in nature, that is called the nanofluid. So when these nanoparticles mixed with this base fluid, then both thermophysical properties of the nanoparticle and base fluids, they are combined, and generally the thermophysical properties of the combined nanofluid will enhanced. And that's why this nanofluid applied in different places. Now, when we are talking about this nanofluid, we generally observe that different type of base fluid and different type of nanoparticles in general used in industries. Some of them you can see here. Base fluid, the base common is the water, otherwise ethylene glycol or engine oil, those are using. And in nanoparticles, they have different pattern, like that metallic. If you go for copper, gold, or iron, in oxide, aluminum oxide or copper oxide or titanium oxide, it comes generally the CNTs, carbon nanotubes, it is single walled or multi-walled. Graphene, those are using, and sometimes we are using the nanodrops. Beyond that also, some cases using the surfactants, generally gum aerobics or CMC. So when we are check the thermophysical properties, we can see this is different values we can observe here, and this is for the nature. When we are applying the industry, we can see which one is more suitable for which kind of industries. So that is how we can distinguish them, and also we can characteristics them according to their industrial applications. So there is several techniques or several methodology where we are using this nanofluid concept. Some of them is very common, where we are using the Brownian motion and thermophoresis effect. But some researchers are using the volume fraction concept. So here we basically focus on this volume fraction concept, where phi is represent the volume fraction of the nanoparticle. And using this volume fraction, we can see how the viscosity, density, these are the physical properties, and heat capacity, thermal expansion, or specific heat. The thermal property of the base fluid is changed. And we had many relations. It is based on the different particles, how the dynamic viscosity is changed there. And also there is many models which is based on this thermal conductivity nature. It is a different feature is there, like that if we can using the spherical shape, Maxwell model is very important, but obviously we need to keep a low concentration. If you increase the concentration, then this Brugman model is very good. Sometimes we are using the shape because we know that there are different shape of the nanoparticle. So Hamilton-Crosser model is very important for that one. And recently people are using the concept of nanolayers. So for that Yu-Chui or Zuan model is very important, those cases. So when we are talking about the safe factor, mainly the Hamilton and Crosser model, we had different safe factor values, and also we have the sphericity nature. Here we put a few of them, like that sphere, platelet, cylinder, lamina. Those are very common used. Hybrid nanofluid concept, which mainly our focus here, that is similar concept where basically we are using a single nanoparticles, but if you are using two nanoparticles, then it will be a hybrid nanofluid. That means with the base fluid you can add it to different thermophysical properties related nanoparticle, and that's why it is more attractive nowadays than the nanofluid for the researcher and also for the industries. So when we go for these applications, I told that basically this addition of nanoparticles, it's control the thermophysical nature, mainly the thermal properties. That's why most of the industry where you have you creating heat or heat transfer play a major role. For those cases, this hybrid nanofluid has a huge application, like that aviation, cooling or heating, renewable energy and automobiles. These are very important features here. And if we go for the thermophysical properties, here you can see we consider the same concept of volume fraction. And here we have phi 1 and phi 2. That means phi 1 is the volume fraction of nanoparticle 1, phi 2 is for nanoparticle 2, and this is control basically the thermophysical properties of the hybrid nanofluid. The relations are similar to the nanofluid, but here we are incorporate both nanoparticles feature. So here you can easily see a comparison, and you can easily understand how it is differ for the nanofluid and hybrid nanofluid. I'm not going for this. Let me go for the main idea, which is interfacial nanolayer. Generally, when this nanoparticle immersed in a base fluid, the surrounding of the nanoparticle, these liquid molecules of the base fluid, they are accumulated and they are making a very thin layer. The concept came very late of the applications, and later on many people work on that to implement about the mathematical model. But people realize that this thin layer is very important when we are consider the thermal properties of the nanoparticles. It basically changed the thermal property of the nanoparticle, which is very impactful when it applied in the industries. So that's why recently we can see this interfacial nanolayer concept using many researchers in their literatures. So the concept basically appeared in 1984 by Henderson and Sol, who is find this concept, and then in 1995, Squad et al. They are trying to implement that one in mathematically in this format. Consider the thickness of the layer is in the form of K layer, and Kp is the basically radius of the nanoparticle, and they basically consider the spherical shape, and this is the formulation they are using. But obviously the things are implemented slowly. By Yu-Chui 2003, they are improved this model, and in the form of classical Maxwell thermal conductivity, and they are using the concept of phi, which is basically the improved volume fraction, which is based on the delta naught, which is the radius or thickness of the interfacial nanolayer. Later on, Z et al. They are improved or they are given another mathematical model and shows that how this thermal conductivity of the nanoparticle is depends on this thickness of the interfacial layer. Later, Liang et al. He is proposed another model. He has considered a average concept like that. One is beta 1 plus 0.5 delta. Delta is basically the thickness of the nanolayer. So he take the average in the middle point, and also beta, which is 1 point delta. That is the last region of the interfacial layer. And combined these two and produce a mathematical model, which you can see here. Then we are familiar with this Hamilton Crosser model, which developed by Xian et al. In 2015. He basically developed for the CNTs, carbon nanotubes, and he can introduce this relation where he has considered the shape, basically the cylindrical shape in for the carbon nanotubes, and he has developed the model with thickness of the T is basically the thickness of the interfacial nanolayer, and B is the radius of the CNT, carbon nanotubes. And since this is cylindrical in shape, so that's why he is considered the sphericity constant there. And this is how he improved the model. From this nanofluid, we are moved to the hybrid nanofluid, and we basically extend this Xian model with the concept of interfacial nanolayer, and we upgrade the volume fraction phi1, phi2 with the particle with I1 and I2, which is the fraction of the nanolayer thickness and radius of the nanoparticle. And we can implement the things is like that way. And here we can see, due to this interfacial nanolayer, how different thermophysical properties of the hybrid nanofluid is going to change. So here these few relations you can see here, which we can using different parameters, and finally we can get these relations, which is KHNF with corresponding tau 1, tau 2, and which is depends on obviously the KNF, which is based on the nanofluid. So this model we are going to use in our present study. So generally we are familiar with this presentation of the mathematical model, but let I just go for the basic. When we are going for this hybrid nanofluid model, there is a different parameter which mainly we focused on, like that the geometry of the surface, then the rheology of the fluid, and the governing equation. We sometimes we extended up to energy, and sometimes we go for the concentration equation also. And with that, different other parameters like that boundary condition, medium, and some external impact like that magnetic field, radiation, Joule heating. These are plays a very important role when we are using this or we are improved the modeling for the hybrid nanofluid. Obviously, this modeling is useful for any model on the fluid mechanics. But when we improve this model, we obviously take care about the applications, or based on the applications, we go for different parameters. So in present, I am going to present a mathematical model on unsteady hybrid nanofluid flow over the spinning sphere. So you can see the geometry here, and as usual we had used here the concept of the nanolayer, and we want to see how this thickness of the nanolayer impact on the system. So this is the general schematic diagram of the problem. And when we go for the governing equation, we had the continuity equation, we had the momentum equations, where we had using the Darcy-Forchimier model, and also we are using the magnetic field. In this problem, we are using a simple model, simple non-Newtonian fluid, which is Casson fluid. So that is considered as a base fluid here. And 1 plus 1 by delta lambda is represent that concept. And here we can using the both motion, U momentum and W momentum. And also we are using the temperature equation. Here we are using heat flux, which you can represent the last term of the left-hand side. And also we are using the nonlinear radiation, the second term from the right-hand side, and the third term or last term is related to the viscous dissipation. So the problem is the unsteady problem, and these are the conditions we had used here. Very non-condition convective boundary condition used here. Otherwise, as a ambient conditions are T tends to TH and U tends to UE. So when we use these conditions, we know that when the equation is there, we need to first simplify that one. So for the simplified, we had used the similarity transformation, and this similarity transformation basically transfer this PDS to ODs. So that is what we had observed here. So this is the momentum equation, which is reduced after the similarity transformation. And this is the temperature equation or energy equation, which can simplify it like this way. Obviously, the terms which are appeared here beyond this velocity and temperature part, like that A, ZR, AM, those are the non-dimensional parameters. A is basically the unsteady nature, and K is the permeability, FR is the Darcy-Forchmeyer constant, GR is the Grashof number, and M is the magnetic parameter. Similarly, we can get for the energy equation, tau is represent the heat flux constant, and we can say delta and F is the same what we had see there. And we can see the simplification of the boundary condition, where Bi is represent the Biot number. It came due to the convective condition. So when we have now this simplified form, now we are going to solve this system of equations. So obviously we can go for some physical quantities. So here we had used a momentum equation and energy equation. So that's why here the physical quantity is skin friction and Nusselt number, which we had shown here the form after similarity transformation. And another very important parameter is the entropy, which is basically represent the irreversibility of the system. And so we had calculated this entropy generation. And when we go for the similarity transformation, we can get in this form. For the interfacial nanolayer concept, here we are used two nanoparticles. One is AU and MWCNT. So you can see we had used the same Jiang model. So that is how it is implemented here, and this is how it is improved or it is impact on the thermophysical properties like that viscosity, density, thermal conductivity. We can see here the thermal conductivity. This is how it is impact on that. So this is the final form of the thermal conductivity, which we had getting from the same concept Jiang paper. So we had also discussed this, how this change with phi 1, phi 2, so not go for details. And when we are using this nanoparticle and base fluid or maybe hybrid nanofluid in a combined, we should know what are the physical properties or physical property values of those nanoparticle and base fluid. And you can see here, obviously, it is completely depends on what kind of nanoparticles you are using here. being the different physical properties. And after that, we had used the numerical scheme. There are several schemes out there you can use. Here we had used the finite element approach, and we are discretize the zone with small elements, and then we can study the things. And you can see the results are here. So comparison is the initial stage. We need to check our numerical scheme is correct or not, and for that we need to go for a comparison with some special cases. So here we make the comparison, and we can observe that the numerical scheme is fine, and when it is there, then we can go for different results. And we can see here different results for axial velocity, and obviously different parameters we can use here, like that lambda is the mixed convection parameters, and we can see here when we are using this, or we improve this convection things, that means it is improved velocity. While when we consider the porosity nature, permeability, that means FR, that is Darcy-Forchmeyer parameter, velocity, because for the clear region or clear zone, it is easy for the fluid to pass through, but when you have the porosity or porous region, it will restrict them. And then for the Casson parameter, obviously it is restricted the things because it is created more shear stress there, so it is restricted the velocity. And if you increase the unsteady nature, we can see that the velocity of the fluid will increase. And in all figure, if you see, we had considered this I1 and I2, which is basically the ratio of the nanolayer thickness with the radius of the nanoparticle. And when we observe that, we can see that when this nanolayer thickness will increase, that means if you increase your I1 and I2, that means you basically control your axial velocity of the fluid. Similar way, we had seen that nature of the transverse velocity. Obviously, we can go through the same parameters, and we can observe almost the similar nature here. And the thing is that the nanolayer thickness also shows the similar concept. That means it is try to control the transfer velocity of the fluid also in this case. When we see the temperature, here we can change the parameter. Tau is basically the heat flux, and when we are consider this heat flux, Catanov heat flux, obviously we can see that it is basically put additional heat in the system, so it improved the temperature of the system, and that is what we had observed here. Otherwise, if the unsteady nature and the Casson parameter nature, this basically see that control the temperature of system. And you can see in
Dr. Shaw?
Yes.
Sir, I'm terribly sorry to interrupt, but we are actually running out of time. So,
okay, let I try to conclude.
Please take your time.
Yes.
Sure, sir, sure.
So, similarly, we can see these physical properties. We try to plot into 3D. So, we can see the similar nature. I think we are familiar with most of them. And also we discussed the entropy generation. But each cases, our main focus was how to this interfacial nanolayer impact on the system. So everywhere we try to compare with those things. So in conclusion, we can see that how the same things is written here, that it is controlling the system, and how this interfacial impact. So further direction where we Obviously, there is many ways you can progress in this direction. Like that, you can choose different fluid rheology. You can choose different boundary conditions. You can choose different numerical scheme. Obviously, if you go for a new test like that, presently people are using in artificial neural network, those things. Then you can go for the higher nanofluid, like the ternary or event properties of the nanoparticle. These are some future progress nowadays you can observe in this direction. These are a few references. And these are group working with the students and with the collaborators. So thank you very much, and thank you very much again. Mainly, I need to thank to Dr. Eva to give me opportunity to present my work. Thank you very much.
Sorry, I think I had done.
I think I had done.
Does anyone have any questions? It was very interesting talk.
Does anyone have any? It was a very interesting talk.
Is there any question from the audience?
Is there any question from the audience?
If not, then we are going to proceed to the next talk.
If then we're going to stop.
Okay, thank you very much.
Your time.
So for the next session,
we have Professor Apala Majumdar. Professor Apala Majumdar is appointed as a professor at the Department of Mathematics and Statistics, University of UK. He is an applied mathematician by training with expertise at the interface of mathematics. Further specializes in mathematical modeling of pneumatic liquid crystals and quantities, including their applications in industry. Course this new type of multi-scale theories that focus on the multi-scale theories that focus on
equilibrium phenomena and modeling of software-based applications in industry and technology. Being the inherently interdisciplinary nature of a research, she has worked with pure applied and industrial mathematicians, worked with physicists, chemists, and researchers from the industry. She has several international collaborators, and her work is currently funded with different international projects. Prior to her appointment as chaplain, she had worked at the University of Bristol, University of actually, this talk was created. Actually, we are seeing the first one and all of the slides. Not the slides from here. I think that was the Ma'am, can you please control that? Yes. Welcome to Chile.
I work as a professor of applied mathematics at the University of Strathclyde in Glasgow in the United Kingdom. Before I start, I really like to thank Dr. Atul Day for initiating this conference and inviting me to speak at this conference on applied mathematics and science and engineering at SOA. Now, as you can tell from my title, I mainly work on the mathematics of material science, the mathematics of soft materials or liquid crystals. Now, before I start, I'd like to tell you a bit about myself. My main job description is that I'm an applied mathematician working at Strathclyde in Glasgow, but I'm also the associate for international research for the Faculty of Science. And the faculty is one of my jobs, it is one of my responsibilities, international partnerships around the world. In terms of my scientific expertise, I mainly work on the mathematics of materials science or liquid crystals. Mathematics is basically continuum mechanics, nonlinear partial differential equations, scientific computing, and also functional analysis. So my work is very interdisciplinary. I've worked with physicists, chemists, and researchers from industry, and then luckily it's also very international. So I've worked with people from China, India, obviously around the continent, and North and South America. So in that respect, I've been quite fortunate. So here is a bit about my institution. So the University of Strathclyde is really located in the heart of the city, in the middle of the city centre in Glasgow. It was established in 1796. We have about 25,000 students and almost 4,500 to 5,000 members of staff. We have 4 different faculties: engineering, humanities, social sciences, science, and the business school. And we're also very much known for our entrepreneurship. So we were the European Entrepreneur University of the Year in 2023. And almost 90% of our research is rated world leading or internationally excellent according to the current REF, or the Research Excellence Framework exercise in 2021. So if you want to know more about Strathclyde or my research program, please do feel free to contact me by email after the talk. So moving on to the science, I understand that this is a 30-minute talk, so I will skip most of the technical details and try to give you an overview of what I actually work on. So liquid crystals, what are they? So liquid crystals, as the name suggests, these are materials that are somewhere between solids and liquids. So they are more ordered than a conventional liquid, but less ordered than a conventional solid. So they basically combine fluidity with the ordering characteristics of a solid, and what you get in between is a liquid crystal which has properties of both states of matter, which is really a functional material, a soft material that is very responsive to its environment. There are many different kinds of liquid crystals: pneumatics, smectics, and cholestrics, but for the purposes of this talk, I will only focus on the pneumatic phase. So pneumatic liquid crystals, they are the simplest kind of liquid crystals, but they're also the most commonly used. So if you look at the picture, at a very basic level, the pneumatic molecules, they're elongated or the shape of ellipsoids. And these elongated molecules, they move around freely as in a normal liquid, but whilst moving around, they tend to line up along locally preferred directions. So these are basically directionally ordered complex fluids. So these are complex fluids with certain special directions. Pneumatic liquid crystals have many applications in science and industry. Most of you have heard of a liquid crystal display. So pneumatic liquid crystals are actually used in your laptops. So your laptops have pixels inside them, and the pixels are usually pneumatic liquid crystals, and these pneumatic liquid crystals basically respond to external electric fields or power or incident light, and they basically control to some extent the performance of these electro-optic devices. The pneumatic liquid crystals are now also used in biology because many biosystems have this elongated constituent molecular structure. And these elongated molecules, they tend to line up with each other, so you can model these biosystems using tools from liquid crystalline theory, because they have liquid crystalline structures, or they have these alignment profiles. They're also used in sensing sensors, and that's because pneumatic liquid crystals are very sensitive materials, so they can easily sense external agents like biomolecules or lipids or any sort of external agent. And because they can sense these external agents, you can use them as sensors. They're also used in active sort of study of active systems. So active systems, they basically convert chemical sort of energy into mechanical work. So they are constantly out of equilibrium systems, and they convert this intrinsic chemical energy into mechanical work. And active systems are also used in mechanobiology now. So you can use them to understand the mechanics of biological systems like your cell cytoplasm biology. Liquid crystals, they've also been used for security applications. So you can use liquid crystals to design labels, and these labels can be used to identify objects of value. And here you have an example of a QR code which is manufactured using liquid crystal droplets, and they're fairly robust and they stand the test of time. Now, the focus of my research program is that I mainly work on the analysis and the applications of the Landau-Dijon theory for pneumatic liquid crystals. Now, the Landau-Dijon theory is one of the most powerful mathematical theories for pneumatic liquid crystals. So, in fact, it was one of the reasons for awarding Dijon the Nobel Prize for Physics in 1991. So, like I've already told you, pneumatic liquid crystals are basically complex fluids or complex systems with preferred material directions. Density is two separate contributions. The first contribution is what we call the bulk potential. This basically accounts for thermodynamic effects. This dictates phase transitions, spatially homogeneous samples, for example, the transition from a disordered to an ordered pneumatic phase as a function of the temperature. And then you have the elastic energy density, which basically penalizes spatial inhomogeneities in the system. So the bulk potential depends on the Q tensor, or the eigenvalues of your Landau-Dijon Q tensor order parameter, and the elastic energy density depends on both the Q tensor order parameter and its gradient. And as is standard in most problems in the calculus of variations, the modeling hypothesis is that the physically observable configurations, the ones that you might expect to see in practice in a laboratory or for an application, they are basically modeled by either local or global energy minimizers. So they are in fact classical solutions of the associated Euler-Lagrange equations. And this is a basic exercise in the calculus of variations, that you can derive the Euler-Lagrange equations. And if you look at these formulae, you will see that the Euler-Lagrange equations, they are basically a system of 5 nonlinear elliptic coupled partial differential equations. And therefore, when you are studying applications or when you are modeling confined pneumatic liquid crystalline systems at a mathematical level, you're really studying boundary value problems for a system of nonlinear elliptic coupled PDEs. So that is the essential mathematical.
Approval दीजिए. Refresh करो.
particular, if you take of two-dimensional solutions, say on a square domain, under certain special circumstances, you can stack two-dimensional solutions on top of each other to generate a real 3D solution of your Euler-Lagrange equation. This kind of stacking procedure is quite special, it's quite specialized, but in certain special circumstances, you can stack two solutions on top of each other, so there are certain compatibility conditions. You can stack them in a particular sequence, so you need a special sequence and you need compatibility conditions, but if you can identify the sequence and the compatibility conditions, you can put them on top of each other and you can solution like we have here. So here on the bottom you have a diagonal solution, on the top you have another diagonal solution, and in the middle you have another 2D solution which we call the well-ordered reconstruction solution. Similarly here, diagonal on the bottom, diagonal on the top, and the BD in the middle. So I will finish now very quickly by telling you about some work that we did with experimentalists, just to give you an idea of what mathematics can actually achieve. So this is work done with an experimental group at the University of Luxembourg, Professor Jan Lagerwald. So they can make liquid crystal droplets. So a droplet is a three-dimensional geometry, right? And a droplet has two surfaces, an inner surface and an outer surface. Now these are experimental images, so you can see these droplets under a polarizing microscope, and you can see these twisted black brushes, and these twisted black brushes are defects. Now the question is, can we model these liquid crystal shells, and can we reproduce these twisted defect structures which manifest as these twisted black brushes? And the answer is yes. You can use a Landau-Dijon free energy approach. It looks quite complicated, but once you get used to it, it's not so bad. You have these parameters. T is the reduced temperature. This is a measure of the size of the droplet. How big is it? The inner radius and the outer radius and the aspect ratio and some material properties. These are the boundary conditions. Again, you can set up an optimization procedure to calculate energy minimizers, or you can even solve the Euler-Lagrange equations if you want to understand the full energy landscape. And if you do that, you can recover the stable solutions of your Euler-Lagrange equations or the energy minimizers. And these energy minimizers indeed have these twisted defect structures. You can see them on the top panel on the right, the twisted defect structures, which you can map to the experimental counterparts on the left. So on the left, if you look at panel H, you see these twisted black brushes, and you can make a qualitative correspondence with the twisted defect structure on panel A on the right. At the extreme right, you can see the twisted white lines, which are reminiscent of the twisted dark brush. So my main message, I do have some other work. So this is again nematic shells, but these are shells filled with a different liquid crystal material. So this work has been published in Nature Communications, so we are quite proud of it. But the message remains the same. You can use a free energy with the right scalings and the right number of parameters. So the temperature, the size of the shell depends on the inner and the outer radius, and also some material and isotropy parameters. But if you set up the free energy properly and the scalings, and you identify the right parameters, and you can identify some experimentally relevant values for these model parameters, you can either use a numerical optimization procedure, or you can solve the Euler-Lagrange equations using various numerical methods or analytic techniques. And if you do all of that, then you can recover experimentally observed textures. You can gain some insight into what causes multi-stability and what causes the sort of textures that you observe in experiments. For example, here the highlight of our work was that we could capture these focal conic domain structures, these football-like patterns, which you also observe in experiments if you look at these pictures here. So I think that brings me to the end of my talk. So what I'm really trying to tell everybody is that liquid crystals, they are mathematically very rich because they span a range of mathematical subdisciplines from mechanics, geometry, topology, nonlinear PDEs, scientific computing, numerical analysis, but they have a real impact in real life. I mean, you can actually use mathematics to drive approaches to design new materials, new systems, and new applications. So it's a real opportunity for mathematicians to make an impact outside mathematics. So I should thank everybody who's funded my research, and of course the conference organizers and Dr. Dave for really being very organized and he and being very sort of systematic with his communications. So I found this entire experience very smooth sailing. So I'd like to thank us for that. So I'm now happy to take questions if there are any.
Is there any question from? Is there any question? Well, I don't think there is any question yet. In case there is some question, you can contact ma'am. Her mobile number is there. And I thank you, ma'am, for that enlightening talk. You have shown us there's more to mathematics than we actually see. And we are going to follow your footsteps and go into other fields apart from mathematics to see where it leads us. Thank you very much, ma'am.
Bye-bye. Bye.
Thank you. Bye. Local places like the Dhoni temple. Okay. So for now, we are going to have the tea break upstairs, and after that, we will take the bus and go to the local trip. Following which, we are going to have the cultural program and grand dinner. Okay. Thank you, everyone. बंद कर दूं क्या?
Please, please.